Hey everyone! Today we will be doing the annotated flash attention. So this will probably be one of my most important videos yet, as you know, the flash attention algorithm is essentially the backbone to every single transformer, every single large language model out there today. And that's because it enables us to train long sequence length problems with limited memory usage. Now, to do a proper flash attention implementation, we need to write fused kernels, right, in either Triton or in CUDA. So the next video will actually be a re-implementation of flash attention, both the forward pass and the backward pass in Triton. Today, we're not going to be doing that because I think it's just a little bit too much of a prerequisite, and I want this to be as accessible as possible. So as long as you know some PyTorch or NumPy, you're good to go. You have all the prerequisites here. And the math is also relatively simple. We'll kind of step through that as well. So the difference between what our Triton implementation later will look like and the PyTorch NumPy implementation today is that when we write fused kernels, when we write things for the GPU, lots of things happen in parallel. We can go ahead and perform multiple operations at the same time, and that's how we set things up for Triton or CUDA code. In PyTorch, we don't really have that ability to just like run multiple operations at the same time. So we're going to have for loops. And of course, for looping through something or parallelizing the same things that we would have for looped will do exactly the same operation. It's just, of course, it'll be faster in Triton. This is mostly just to understand the algorithm and take a look at what happens. So this video is basically going to be a ton of visuals of just understanding what is even going on and then implementations to kind of go along with it. The other thing, if you find this video or any of my other videos helpful in any way, please do become a member. It helps support the channel, helps support this content as I'm just doing this all on my own. So just let me know if you have any questions, comments, concerns down below. But let's just go ahead and get started with attention. So we're going to be doing a little bit of a recap, a quick recap of attention. I already expect that you know the attention mechanism. If you don't, I'll link a video down below. You can learn the more minute details about attention, but let's just step through it real quick. This is the standard attention formula as described in the attention is all you need paper. And essentially, it's just QK transpose divided by some constant. This is the square root of the embedding dimension of our data. We do the softmax along the rows of the attention matrix and we multiply it by the values. What that looks like essentially is our data. There's of course a batch dimension. Let's ignore that for now. We have some sequence length by embedding dim, where essentially you have a sequence length, different time steps of data or different tokens or whatever this may be. And every single time step is represented by a vector of length embed dim. And what we do is we first take this data, project it with 3 separate learnable projections to produce queries, keys, and values. We go ahead and take the queries, the keys, we transpose the keys, we do the mapmul between them. This is a sequence length by embed dim by an embed dim by sequence length, producing a sequence length by sequence length attention matrix. And this attention matrix is dot product similarity, right? So the value, the actual value of this position is the dot product of how the first token is related essentially to itself, which isn't that interesting, but it's there. This specific value is the dot product similarity of how the third position was related to the second position. And overall, we essentially end up with a pairwise relationship of how every single time step is related to every one of the other time steps. We then go ahead and divide by this square root of the embedding dimension. The reason is when we do this, we're essentially multiplying an embed dim vector with an embed dim vector, right? That we're doing the dot product between the two. When we do this, the variance of our output, basically the variance of these outputs, will be scaled up by embed dim. And so we're going to scale it back down by dividing by the square root of embed dim, which if you divide by a, you're really dividing the variance by a squared. So this is just to make our training a little bit more stable. Now that we've done that, we go ahead and take the softmax along the rows of this attention matrix. So basically you take the softmax of the first row, second row, third row, fourth row in this case. And the only differences was in these representations, these were essentially the raw dot product values of QK transpose. Now, each of these rows essentially add up to 1, right? We just did the softmax along these rows, so each of these rows add up to 1. We then go ahead and take this and multiply it with our final values. And what that looks like is this. We'll get a sequence length by sequence length multiplied by a sequence length by embed dim, giving us a sequence length by embed dim. And the relationship is this. To get this specific vector here, this is essentially the multiplication of this first value, this weight here, times this vector, plus this times the second vector, this, the third vector, and then the fourth vector. So it's simply a weighted average. Remember it this way. These 4 weights that we're looking at here add up to 1. That's the first condition. And we know that this position is how is the first token related to the first token related to the second token, third token, and the fourth token. Basically, those are the weight values. How was that first token related to all other 4 positions? And let's just say these weights are 10%, 20%, 30%, and 40%. And so if my attention matrix says that, hey, this first token is related to itself by 10%, the second token by 20, 30, 40, well, this is the vector representing the first position. This is the vector representing second position, third position, fourth position. So let's take 10% of the first one, 20% of the second one, 30% of the third one, and 40% of the fourth one, add all of those accumulations together and get this output. What this really means in practice is that the input, the sequence length, along the sequence length, each of these time steps was a representation of the time step. Like this is the representation of the first token, the second token, third token, so on and so forth. Now what we have is this is a representation of how the first token was related to all the other tokens, and we did a weighted sum. And so this is essentially a context vector of the representation of the first token to everything else. This second one's a context vector of how the second token was related to everything else, so on and so forth. There are a couple of small extensions. The first one, of course, is multi-head attention. When we do these representations of how one time step or one token is related to other tokens, in complex problems, tokens can be related to each other in a variety of ways. There isn't just one way things can be related to each other. So instead of doing sequence length by embed dim, mapmul with embed dim by sequence length, let's chunk it up. We're going to only look at the first half of the queries embed dim and the first half of the keys embed dim. And then a secondary operation is going to look at the second half of the query embed dim and the second half of the key embed dim. When we do this, we'll end up with a separation like this. We'll essentially have exactly what we had earlier, but now we have sequence length over embed dim over 2, embed dim over 2 by sequence length, and this is going to give a final sequence length by sequence length attention matrix. But we won't have just one of them, we're going to have 2 of them because we've split the embedding dim into 2. Of course, we can go even more granular. We can split it into 4 if we want, so we'd have 4 different things here. And what we hope is with a sufficiently challenging problem, these different attention matrices will learn different types of relations of how these words are related to other words, or different tokens are related to other tokens. The other extension, of course, is the group query attention. This isn't something we're going to be looking at today or implementing today, just to keep the PyTorch implementation as simple as possible, but the idea is pretty simple. Essentially, instead of having keys, basically we're doing the mapmul between some chunk of the query and some chunk of the key. Instead of having a one-to-one relationship for every chunk of query, we have another chunk of key. Let's reuse some. So this first chunk of query is going to mapmul with this first chunk of the keys. The second chunk of the query is going to mapmul with the second chunk of the keys. The third chunk of the queries is going to mapmul again with the first chunk of the keys, and we just rinse and repeat, right? So we can see that there's some parameter reuse here. And this is the official figure from, the group query attention, where every single query in standard attention is matched with a key and a value. But now what we have is for every 2 queries, we'll have a single key, or every 3 queries, or every 4 queries, like whatever the grouping strategy you want is. Again, this is a minor detail. We'll look at it when we actually implement the Triton kernel, so we get these additional features in there, but for today, we're not going to really deal with this. Another extension, of course, is causality. Large language models are causal. They're generative models. They look at only the past to predict the future. But like we saw, this vector here is a representation of all the time steps. Basically, the first weight times the first word, second weight times the second word, third weight times the third word, and the fourth weight times the fourth word. This means for the first position, the first token's position, we're learning representations not about just the first token, but future tokens as well. And that's a bit of a problem, right? Because essentially what that's saying is that we're looking to the future. To learn something about the first position, we're looking to the second, third, and fourth position. And so what we typically do is we do a causal mask, right? We mask out these top parts. So when we do our mapmul now, it's going to be the first weight times the first position plus 0, because this is zeroed out, times second position, 0 third position, 0 fourth position. So we're essentially zeroing out the contributions of future positions. And then if we move on to a different time step, right? So if the third one, we know that the third time step here can only be a representation, if it's causal, of 3 and earlier. So we're doing the first position, or first weight for the first position times the first weight, first vector. Second weight, second vector. Third weight, third vector. But the third position can't look into the fourth one, so we do the 0 times the fourth vector to remove that contribution. So here's essentially the full flow, right? We have QK transpose. We mapmul them to get an attention matrix. We take the softmax along the rows of the attention matrix to get this. We then mapmul this with our values to get the final output. And this is essentially the full flow. And to get a little bit better idea of how this all comes together, if we want specifically this output, this vector, only this vector in the output, we know that this vector of the output is the mapmul of this vector of our softmax attention, basically the weights themselves, with all of the values, right? All of the values. Go back, all of the values. And then to get this specific vector here, we need to take the softmax of this row of our attention matrix. And to get this row of the attention matrix, that's the mapmul of the first query with all of the keys. So that's the flow, right? To essentially to get this position here, to compute everything we need for here, we need all of the values. We need the first row of the softmax attention, which means we need the first row of the attention, which means we need all of the keys, and we need the first query. So there's a little bit of a correspondence here. Whichever row of the output we need that specific query. And we need all of the keys and all of the values for all of these operations. And this is gonna be really important a little bit later. Here's the issue with attention. What if L is an extremely big matrix? Let's say L was 1,000, which isn't even that big. That means L by L contains 1,000,000 elements in it. So here's the problem. Our attention matrices here are enormous for long context lengths. Imagine that the L here is 128,000, which is a pretty common sequence length for a lot of the state-of-the-art neural networks, frontier language models out there today. That means the total attention matrix here would be 128,000 squared. That is a ton of elements here. And this would use up a huge amount of GPU memory. And this is exactly what flash attention is going to solve. And so essentially, think about it this way. Our input and output is sequence length by embed dim, which can be a big tensor, but not nearly as big as this, because in standard cases, sequence length is, let's say, 128,000 for the big LLMs out there, and the embed dim is typically like 4096 or 8192 or something like that. So this is essentially at the most, 128,000 by, let's say, 8192. This is 128,000 by 128,000. Absolutely enormous tensors. But our output is the same as the input. The output is also sequence length by embed dim. So the input and the output shapes are identical, but we have to go through these massive intermediate, and not just one of them for the attention matrix, but also the softmax of each of those rows. We need to go through these massive intermediate representations to make this work out. And so that's exactly the problem. If L is really big, we essentially, in the standard naive attention implementation, we materialize in memory these massive internal L by L matrices that we would rather not. And that's what we're going to be working on today. So what if we never compute the full attention matrix? Okay, how would that work out? I know that to compute this specific vector, I essentially need to do this weight times this vector here, plus the second weight times the second vector, third weight times the third vector, so on and so forth. Well, to get this weight, I just need this value, right? And for this value, I just need Q times K transpose, right? So I can just loop through, grab the next one, grab the next one, grab the next one, right? No, that is not how it will work. If it worked out that easily, this would not even be that interesting. It unfortunately does not work out that easily. And you can probably tell what the issue is. To compute the softmax, if we want this specific value, essentially we want one of them at a time right now, right? We're going to loop through them one of them at a time. Even if we just want this one value here, we need to compute the softmax of this entire vector, which means we need all L elements on this vector. And so that's a bit of a problem because we can't really just do this iterative method that we want to do. And the reason for that is softmax. Softmax is a vector function. Essentially, what we're going to do is for every single element, we're going to subtract the maximum. Remember, we subtract the maximum from every element here, the max of the vector, and this is a numerical trick for softmax. Softmax, again, is a shift invariant function. You can take a vector and add or subtract any value you want to it. In our case, we're doing the constant of max, but as long as some constant, you can shift it however you want, but the output softmax is the same. And you can easily prove that to yourself as this is e to the x times e to the negative max. We have e to the x times e to the negative max. Negative max is a constant, or e to the negative max is a constant that pops out in the front, and then the denominator e to the negative max and the numerator e to the negative max will just cancel. So that's an easy proof there. But the problem is this. We need the max of the vector, and we need the sum of the exp x minus max of the vector. So to compute either one of these things, we kind of need the whole vector. But if we don't have the whole vector, then what do we do? And this is exactly the problem. We need the entire vector. We need the max of the vector and the sum of the exp every element minus the max of that vector just to get this one value here. And if that's the issue, then there's really nothing we can do about it. Or is there? We are on the right track. This entire notion of not computing the entire attention matrix, but just computing pieces of them at a time, the piece that we need. In this case, we only care, in this specific iteration, we only care about this value here. If somehow we can compute what this is, we're good to go. It's really the trick of how do we do that. But we never, if we can iteratively do it, we never have to materialize the entire L squared tensor. Of course, if you have like unlimited GPU memory, this is kind of a wasteful method. Anything that's iterative, that doesn't just load everything to memory and vectorize it and all that sort of stuff, is slower. But in the case of flash attention, we purposely need it for long context lengths that can't fit in GPU memory. And that's why it's so fast, because we can actually process it in limited memory usage. So how do we get around this? This is the Online-Softmax algorithm. So we're going to take a look at the details of this in just a second here. But the idea is this: if I want to compute the softmax of a vector, but I can't load the whole vector to memory because it's too expensive to do so. Imagine this vector again has 128,000 elements in it. How do we do it? We need an iterative way to compute our softmax without loading the whole thing in memory. And that means we need to compute softmax by just looping through it one element at a time. So let's go ahead and first derive and then implement Online-Softmax. And this will essentially be the precursor to flash attention, because flash attention is just a reimagination of Online-Softmax. All right, so let's just go ahead and figure this out. How can we do this? So we're doing the softmax of some xi, where let's say x hat is some vector that's x1, x2, xn, right, n element vector. And what we're going to do is essentially the softmax of one of the values is simply just going to be e to the power xi minus m divided by the sum over j equals 1 to n elements, e to the power xj minus m, where m is the max, the largest value in this vector, max of x hat. And what we want to be able to do is compute the softmax of this vector without ever explicitly loading the entire vector to memory. So how we're going to do this is this. We have two things. We have mi. It's going to be the max. So these will be running estimates. Let's call that running estimates. And mi is going to be what is my max up to the ith iteration. So essentially, we have x1, x2, x3. We're just going to for loop through this list of values one element at a time. And mi is my max up to whichever element I'm currently on. So it's going to be max of x1, x2, x3, up to xi, where I is less than or equal to n, right? So whatever iteration we are at until we get to n. And then we're also going to have di, which is going to be the sum of j equals 1, j equals 1 to n. And actually it won't be up to n, it'll be just up to the ith iteration, so because we're on di, of e to the power xj minus, again, mi. And there we go. So this is a running estimate of my max, like what is my max up to this specific iteration I, and this is what is my sum up to this specific iteration of I. And here is the problem. This all sounds well and good, but it doesn't actually work out this nicely. So let's kind of start from there. So what we have, let's just write it like this to make it very clear. We have di is equal to, like I said, sum of j equals 1 to I of e to the power xj minus mi. And what's the next iteration? Di plus 1 will be the same thing, right? J equals 1 to I plus 1 of e to the power xj minus mi plus 1, which we can technically write, I mean, there's no reason we can't. We can write this as the sum of j equals 1 to I, just up to I. So we're going to do, so this is a sum up to I plus 1. We're just going to run it as a sum up to I, e to the power xj minus mi plus 1. Plus, we only did up to I, so we have the I plus 1th term as well. So e to the power x, I plus 1 minus mi plus 1. And here is the issue. This is what I have right? So essentially it's an iterative update. di is what I have up till now. I've iteratively computed up to di. di plus 1 is my next iteration. So this term is the new term. This is the new term, as we can see, xi plus 1. This is what I want, right? This is what I want. And unfortunately, what I want and what I have are not the same thing, because we can see this is e to the xj minus mi, and this is e to the power xj minus mi plus 1. So our value here, but what we're subtracting is different, because mi may not equal to, it could, or it may not equal to mi plus 1. So for example, when would it not be equal to? Let's say our list is 2, 3, 8. Let's just say that's what it is. And we're currently at 3. So my max up till here is 3. So we've done, and actually, let's not even look at 3 values, as that'll make it more confusing. Let's just look at 2 values. Let's say we're looking at 3, 6, and there's other stuff in the future, but we don't care. But when we start out, the max here is going to be 3, right? That's the max. And so di, this is mi, is equal to 3. So m1 is equal to 3 essentially. And d1, so we'll call this m1, is equal to 3. d1 is going to be equal to e to the power 3 xj, whatever term we're on, minus 3, whatever the max is. That's just going to be 1. It doesn't matter. E to the power 0 is 1. Let's go to the next iteration. m2 is going to be equal to, well, 6 is greater than 3. So my new max, my updated max, as I'm going through step by step, is now 6. That's my updated max. So d2 is equal to e to the power 3 minus 6 plus e to the power, this will be 6, right? The new term, 6 minus 6. But is e to the power 3 minus 6 the same as e to the power 3 minus 3? Of course not, right? There's been a change. And that's because the thing we subtracted at that specific iteration was my max. But in the next iteration, I've updated my belief, right? I've updated my estimate of the max, and my new max tells me that, hey, 6, at least up till now, was the biggest value, not 3. And if 3 is not the biggest value, what we just did here is incorrect. We've done the incorrect subtraction. And so we need to somehow adjust for this. And that's essentially it. Of course, if we do it the other way, if we go the other way, let's say it's 6 and then 3, then things kind of work out quite nicely, right? Because in this case, it'll just be our initial max, m1 is going to be equal to 6. And then we're going to have, again, e to the power 6 minus 6, which doesn't really matter. That's just going to be e to 0, which is 1. And then m2 is going to be equal to, well, what is the max of m1 equals 6 and 3? Well, it's still 6. Right? My max has not changed. And so this will be e to the 6 minus 6 plus e to the power 3 minus 6. And so now we can see this term and this term matches. And so essentially that's the case. We have 2 different cases here. If mi is equal to mi plus 1, that's one case. And if we have mi does not equal to mi plus 1, that's a different case. And both of these cases have to be handled. So let's go ahead and do the second case first, as that's the more interesting one, when things change. If xi plus 1, my new term, is greater than my current running max, that means we've updated, right? That means we've updated as, just like we saw earlier, right? If the new term is greater than whatever my running max is, then the new term is my new max. And so we have di is equal, and let me not do this in red so it doesn't look as scary. We're going to do it in orange. di is equal to, this is what we had, so j equals 1 to I, e to the power xj minus mi. That's what we have. This is what we have. What we want is di is equal to sum j equals 1 to I, e to the xj minus mi plus 1. Remember, we split it up, right? We have the old stuff and the new stuff. And so the old stuff, we have it as mi. What we wanted was mi plus 1. So we need to adjust it. And that's exactly what this is. So this is just the sum up to the ith term, assuming that mi plus 1 is my current max. So this is how we're going to adjust it. And so what we're going to do is essentially this. Let's just look at this term specifically. We're going to write e to the xj minus mi plus 1. Well, we can write this as e to the power xj minus m, and actually let's do it this way. let's go the other way just so it's more easy to understand. So what we're going to do is e to the power. What do we have? We have e to the xj minus mi. That's what we have. So let's make it what we want. So we're going to do e to the xj minus mi plus 1 plus mi plus 1 minus e, or not minus, just minus mi. This doesn't break anything. We just subtracted something, added it back. And mi plus 1 is just it's technically just a constant, right? It's just whatever the running max is. So this doesn't break any math. And so then we can write this as e to the power xj minus mi plus 1 e to the power, because this is basically this plus this. So it's e to the power a plus b, which is e to the a times e to the b, right? So split it up that way. Mi plus 1 minus mi. All we've done is we've separated it. And let's quickly check here. Is this not what we wanted? Xj minus mi plus 1. This is exactly what we wanted. And this is an adjustment term, right? This is our adjustment factor. So what we have essentially is this. We want this, so we're going to write it exactly like that. We're going to do e to the xj minus mi plus 1, which is what we want, is equal to this here. So it's going to be e to the power xj minus mi divided by this term right here, the adjustment factor, because it's a equals b times c. So b is equal to a over c, right? Just dividing. It'll be mi plus 1 minus mi. And we can kind of simplify this a little bit more. E to the xj minus mi. And this will be e to the mi minus mi plus 1. Right? Because this is in the denominator, we can just put in the numerator by flipping the sign. So instead of mi plus 1 minus mi, now it's mi minus mi plus 1. That's it. And so this is what we want, e to the xj minus mi plus 1. This is what we had, and this is we're going to call it alpha, but it's just our adjustment term. It's an adjustment term. So let's add those sums back in. So from earlier, we had the sum of j equals 1 to I, e to the power xj minus mi plus 1. And this is equal to the sum j equals 1 to I, e to the power, so this is what we want, right? This is what we want with mi plus 1. But we just showed that mi plus 1 is really just e to the power xj minus mi. This is what we had, so no problem there. That's what we've computed up till now, times e to the mi minus mi plus 1. We've just proved that, right? We just showed that. We just threw these extra sums back in, right? We just toss those back in, but it's no problem. We just showed this. And so now what we can do is very simple. Notice that this is a sum on j, and there's no j term in this, so we can pull it out as a constant. So this is equal to just e to the mi minus mi plus 1. And the sum, this right here, all of this, the sum from j equals 1 to I, e to the xj minus mi, didn't we just have a term for that earlier? That's sum from j equals 1 to I, e to the xj minus mi. That's di, right? That is exactly di. So this is just going to be di. And this is j equals 1 to I, e to the xj minus mi plus 1, right? So this is our adjustment term. Good. So let's go ahead and wrap it up then, right? So we're at the end of this now. We saw earlier that the sum of j equals 1 to I plus 1, which is again di plus 1, is equal to this. And it's going to be essentially e to the power xj minus mi plus 1, just like we had. We split this up into two cases, or not two cases, we just split the sum up into the old terms plus the new terms. So j equals 1 to I, e to the xj minus mi plus 1, plus the the I plus 1th term, e to the x I plus 1 minus mi plus 1. And this piece right here is this piece right here. And so that's just going to be equal to e to the mi minus mi plus 1 di plus e to the x I plus 1 minus mi plus 1. And so di plus 1 is equal to all of this stuff by this update rule. And that was pretty straightforward, right? So we can see the math is very easy. We can do one more simplification. We know that in this case, xi plus 1 was greater than mi. That means mi plus 1, my new max, is just going to be the max of mi and xi plus 1, which is just equal to xi plus 1. So technically, this is e to the power xi plus 1 minus x plus I plus 1. So it's e to the power 0. So technically all of this is just 1, just like that. And so what we have is essentially is the old di multiplied by some adjustment term, which we're going to call alpha, plus 1 for that new term. We have, of course, the second case, which is a little bit less interesting. The second case is where xi plus 1 is less than mi. In this case, my mi plus 1 is equal to the max, right? Again, the max of what was my current estimate for the max, what's my new x that I'm looking at, and this is just going to be equal to mi because, mi plus 1 is just mi is less than, mi is going to be greater than our xi plus 1. And in this case, nothing really changes, right? We're just going to simply have di plus 1 is equal to di plus e to the x I plus 1 minus mi plus 1. And why is this? Remember, di is my sum. It's my running sum up till now. And we just saw that my mi I've used up till now in di, and my new mi plus 1 are equal to each other, which means the thing that I was subtracting to be my kind of iterative max that I've been estimating has not changed. So that extra term, that alpha term we have right here, no longer needs to be multiplied because we're not adjusting anything, because there's nothing to adjust. So we just do this plus our new term. In the new term, it'll be like this, and the old term is just 1, but either way, that's essentially the simplification of all of this. So can we combine these two cases? Because, it'd be nicer to just have this all written out in one statement rather than two separate ones like we have here. And yeah, it's pretty easy. We can just write let's first write mi plus 1 is simply going to be the max, like I've been saying, of mi and x I plus 1. What is bigger? Is mi still bigger, or is my new term bigger? And then di plus 1 is equal to my old my old iterative sum, times my update, my adjustment term, mi plus 1, plus my new term, e to the x I plus 1 minus mi plus 1. And we can check this. If in case 2, for example, if mi plus 1 is equal to mi, so, it stayed the same, well, what happens? This is going to be e to the power 0, because mi minus mi plus 1 will just be e to the power 0 is just 1. Now with di plus my new term, which is what we had, di plus the new term. And in the other case, let me write it back, e to the mi minus mi plus 1. Make the minus clear. There we go. In the second case, or case 1 that we looked at, in this case, mi I plus 1 is equal to x I plus 1, because the new x I plus 1 was bigger than the running sum, so my running max. So my new running max is just that new term, whatever was biggest. And in this case, this term goes to xi plus 1 minus mi plus 1. These two are equal to each other, so this will be e to the 0, this will be plus 1, and it'll be my old thing times my adjustment factor plus 1. And that gives us exactly what we are looking for. And so let's go ahead and first implement what we've seen here, and then we're going to get to some other really important ideas, because the question is, how do we get our softmax from this? Actually, let's just go ahead and look at that first. How do we get our softmax from this? Now that we have these things here. So let's say we have mn, or I'm going to use lowercase m because we're going to need uppercase m for something else later. Mn is equal to this is iterative, right? So we've looped through, but at some point we're going to get to the end of the list, right? We've gone through all I elements, and so we've gone from 1 to n. So here we go. We've gone to n. So once we're at the end, we're going to have the global max, right? Whatever the actual global max of this is. And we're also going to have some dn, which is going to be the true sum j equals 1 to n e to the power xj minus mn. And we're going to have both of these things. Well, what was softmax? The softmax of some term in our list is simply e to the power xi minus mn over sum of j equals 1 to n e to the power xj minus mn. So this dn is my denominator, and this mn is the thing I'm subtracting in the numerator. So really all I'm doing is e to the power xi minus mn divided by dn, and this will go ahead and let me quickly compute the softmax of the values I care about. So we're going to see exactly why this is important, and then a new simplification of this, another simplification called the LogSumExp Trick. So before we get there, let's just implement what we have here before we get too much deeper into this. But if you understand this, we have everything mathematically for flash attention essentially. So you can see it's relatively simple. So what I've provided here already is the naive softmax implementation. So basically for some data that's some batch size by sequence length, so I'm going to say 2 by 8, we're going to compute the max of the rows, subtract the max from every row, exponentiate, take the sum, and then divide it out, or divide the numerator, be xexp by that sum. And this will go ahead and give us our actual, this will go ahead and give us a softmax. So we can see this is the softmax of each of those rows. Not too bad. What we're going to do is write a Online-Softmax method that should give us the same results without ever explicitly like loading everything. Like we can no longer use these vectorized operations like this. We're going to loop through the data one at a time. So Online-Softmax x, and we're going to do mn is equal to x.shape. Output is torch.empty like x, because of course the output of softmax is the same shape, so we don't really have to change anything there. And now we're just going to loop through the data one element at a time. For I in range m, looping through, so we're going to loop through each one of our batch, because I'm not going to vectorize this. We're going to loop through every single sample in the batch one at a time. And let's grab that row. So xi is going to be xi. And we're going to initialize the running things. We need the running estimates for our softmax. And the first one is m. We know m is going to be the max. So we should probably start it out as float negative inf. Let's just go ahead and start out as negative infinity. And the d is going to be a sum. So let's just start that out as a 0. And we're going to essentially add to 0 as we loop through. And we're going to check what's bigger, m, which starts out as negative infinity, or the elements in this list, which will definitely, the first element will be bigger than that. So we should be good. Now let's loop over the elements of the actual vector. For j in range n, we're going to do xj is equal to xi. Grab the jth element in this vector. Just do item for simplicity so we don't have to deal with the tensor stuff. And what we're going to do is store the m previous is m. So prev is m. And then my new m is going to be the max of either m or the jth element, xj. This is basically the xi plus 1 term in the formula. And then d is equal to d times math.exp. We have our adjustment term mprev minus m. So if m and mprev are equal to each other, this term is just e to the 0, which is just 1. So it doesn't do anything. Plus math.exp xj minus m. That's my new term. And then that's basically it, right? So we've gone ahead and done this. Now here is the thing. So what we're going to do for now, just for simplicity, is we're going to do softmax. X is torch.exp. And like I mentioned, what we want to do is take every single element, so xi, we're going to subtract our true max that we've gotten, so m in this case. After all the iterations, m should have the true max of this vector, right? The true max of the vector. And we're going to divide it by d, which should be the true sum of the vector. And then in output I, we're going to store our softmaxed x. And then we're going to return our output. So let's just first take a look at this before we start exploring other stuff. So first we're going to do, let's just make sure these are the same. We're going to do online out is going to be our online softmax rand, and we're going to print our online out as well. What we should see is we all get the same value. So we had an iterative method, but notice that the softmax values that we've computed are the same. Now you might be wondering that what's the gain for this? Because, well, I have the whole softmax here. And the entire point of what we just talked about is we don't want the whole softmax. We don't want the entire row because this row is too big in memory. Maybe I just want the softmax of a specific value. So let's also print out the rand. Right? Maybe I don't want the softmax of the whole row. Maybe I just want the softmax of this element, these elements right here. So index 2. So if I want the probability of these elements, I know it's going to be 34% and 36% because that's, that's what it is. But I don't want to compute the whole vector to do that. I just want these elements. I don't care about the rest because the rest will overload my memory. It's too much. So how can we do that? Well, that's pretty easy because what we've done here, and let's go ahead and do this. We're going to do m. I'm going to call this m is equal to So for essentially, for every single m here, we're going to have a running sum. So let's do m store, call it m store. Don't need any of this, my bad. M store is going to be torch dot, let's do zeros. And we're going to make it in the shape of m. And our d store is going to be torch dot zeros. It's again going to be in the shape of m. So what we've done here is at the end of this loop, so we're going for every single list, for every single vector, we loop through all the vectors one element at a time, like we do here. And then at the end of that loop, we have the true max and this running sum estimate. And we computed these things without ever explicitly loading the entire data to memory. It's a little bit different here because of course we have the whole data in memory. So this is kind of just simulating that idea, but the idea is the same. We've computed softmax without ever explicitly doing these vectorized operations to find the max of the vector, find the exp of the whole vector, the sum of the whole vector, because these things would require us to actually have all of the data in memory. Here we're looping through the elements one at a time, and by looping through it, we're not technically loading everything to memory, because when you write like Triton kernels and stuff like that later on, we're going to like use tl.load, right? So it's not really loading, but just keep that in mind, right? It's not that big of a deal. So now that we have all of this, right, all of this stuff right here, what we're going to do is, instead of just doing the softmax, is this would just compute the softmax directly. Let's not compute the whole softmax. Let's just do mstore, and we're going to store for this specific I, we're going to store the true max of this row, and then dstore I, we're going to store the the true sum that we've computed up till now. And we're going to return mstore and dstore. Let's go ahead and do that. So we're going to do mstore and dstore. Let's print out mstore, print out dstore. And we'll see kind of what we're looking at here. We have our true max. Let's see if this is true. So it's saying that the true max of this vector here is 1.434. Looks like that is indeed the biggest value here, right? This is a negative 0.2, right? This is negative 2.8, so it's smaller. And this is the sum exp of, that entire row that we computed iteratively. So now the question is, given these values here, can I compute the softmax of these values here without explicitly computing the softmax? So I want the softmax of these specific values. I know it should be whatever the probabilities here are, but that would require us to compute the whole row. I just want to compute these things specifically. So let's go ahead and do that. We're going to first do rand, and we're going to just go ahead and grab, for all the samples, we're going to go ahead and just grab the second index, right? Just to keep it simple. So what we've done here is we wanted negative 0.27 and 0.75. So I've just grabbed those specific values here. Those are the things I want to compute softmax for. And then what we're going to do is simply torch. Let's do math. Actually, it is torch. So we're going to do torch.exp. It's going to be this value, right? What we had, minus our mstore. What is the true max? And we're going to divide by the dstore. And now we'll get 0.05, 0.05. Is that what it is? So I wanted the softmax of these two values specifically. Those I know when I compute it for everything, load everything to memory and compute it in a vectorized way, is 5%, 5%. That's exactly what we got here. And that's the trick. Essentially, this online softmax provides me some statistics, m and d. And these specific statistics lets me then go into my vector, grab any element of the vector that I want, and quickly compute the probabilities. So rather than storing all the probabilities in our matrix, we can now go ahead and compute what we need. This is important, kind of going back again, just tying this back, but we're going to come back to this again. I want just the probability of this vector value here. I need a way to compute the probability of this vector without loading everything into memory. So what if I do my softmax, my online softmax method, find the m and the d for this specific vector, and then once I've computed m and d, I'm good to go. I can get the softmax of any value along this vector that I want. Nothing is stopping me. But here is one other trick. This requires us to store a m and a d. We no longer need the outputs here, so let's delete them. M and a d. It would be ideal if we didn't need to store two separate things, but we can half our memory use by just storing one thing. how do we merge m and d together to be one thing? Well, that's actually relatively straightforward. So let's go ahead and do that. So to do this it's called the LogSumExp trick. LogSumExp, it's nothing very fancy. So let's just do this. Let's call uppercase M is equal to mn, basically what was my final max that I got, plus log dn. What happens when I do this? If I do e to the power xi minus m, well, that's writing e to the power xi minus mn minus log dn, right? Just substituting, right? Because these two terms just go there. And that's just going to be e to the power xi minus mn divided by e to the power log dn. And what's e to the power log of something? Well, that's just the something, right? Because they'll cancel. So this is really just e to the xi minus mn divided by dn. And that's exactly what this was, right? That's these two things. Ooh, like that. These two things are identical to each other. So instead of just storing mn and dn separately, let's just do mn plus log dn, store it as m, and then any probability I want, I can simply just do xi minus m, exponentiate it, and I'm good to go. So what that looks like is essentially this. Let's just go ahead and simplify it. We're going to call this L, just to keep the variables different. And L is going to be simply for every single row. So it'll be, again, torch dot, we'll just initialize with zeros. For every single row, we're going to store some value. And in here, we're going to do L. Call it L store again. L store, just to keep it the same. L store is going to be simply m plus math.log d, right? Math.log d. And then we're just going to return L store. And that should do it. So that's it. That's our L store. Let's go ahead and take a look at this then. So now what we've done is instead of having a separate m and d, we just have L store. And let's print out L store. There we go. So we have some values that we've computed right here, no problem. And then let's just do what we want. We're going to do rand, grab specifically those values that we wanted just like earlier. But now all we're going to do is minus L store, and we're going to exponentiate it. So let's do that. It's going to be torch.exp rand, and let's print that out. And let's see if that gives us the same values as before. There we go. So I grabbed these two things here. I know the probability of these things is 30% and 1% based on the vectorized formulation. But now with a single number, one number for the entire row, I can compute the same 30% and 1%. And this makes it very, very cheap. And this is exactly the Online-Softmax algorithm. It allows me to compute one specific value using the LogSumExp trick. And with this one specific value, we can go ahead and compute the probability of any element in the row that we want. Very nifty trick. Now let's just do one quick extension of this. Instead of doing Online-Softmax where we loop through it one element at a time, there's also the blocked method where we basically process a block of them at a time. So we have like basically the first iteration will load the first three elements, then the next three elements, so on and so forth. I'll just paste this in because it's exactly the same algorithm, so it's not that interesting. This is just a little bit of a look into what we'll do in the future, because of course, like when we do stuff in Triton, we'll do stuff in blocks of elements, not just one element at a time. Nothing really changes. So same data, same output, we're gonna loop everything through, nothing here changes. But now instead of looping through J, or looping through this inner list one at a time for J in range n, we're gonna loop through it a block of them at a time. So how many blocks do we have? It's however many elements in the list divided by the block size. And we're going to round up. Reason we round up, of course, is because in this case, we can see that we have a block size of 3. So the first iteration will do these 3. The next 3, if we stopped here, that wouldn't be good. We need to do the next one. But notice that this is a block size of 3, but the next iteration only has one valid element, which means, of course, we're going to have to do a little bit of masking. So the block start is just going to be j times the block size. The block end is just going to be block start plus the block size. The block index is just going to be, the indexes of that specific block. The mask is whichever block indexes are less than n is valid. Anything that's greater than n is exceeding the length of the list, so they're invalid. So we're going to mask them out, only grab the indexes that are valid, load the block, and here's essentially the difference. Now we're going to compute the max over the block. This is a vectorized operation. The difference here is that when we do this load, we're only loading into memory the block of data, not all 128,000 things that are in this vector, just this small block, which means these max, these kind of vector operations, are cheaper. Of course, we're going to have to do them many times as we loop through, but this is feasible as we're only loading this specific block to memory and nothing else. We're going to go ahead and grab the max of this specific block, and then same formula as before. mpref is m, grab my new max, and then my running statistics are the same. It's going to be d times my adjustment term, plus, and here's the difference, before we simply just had a math.exp xj minus xm. That was my new term. But we don't have one new term, we have a block of new terms. We have 3 new terms in this case. And so we just need to do every single one of these elements minus the true max, and then just sum up all the contributions from every element in this specific block. And so the only new thing is we have this new dot sum here. After that, nothing else changes. So the only difference is when we're doing them in blocks, we make sure we do vectorized maxes only within the block, and then we have an e to the xi minus mi. Well, that won't be just for the one xi in here. It's going to be this minus e to the power this minus max, and then plus e to the power this minus max, plus e to the power this minus max. So we have to add up all those things together and just add it to our running sum. Doesn't change anything, but that's essentially it. If you understand Online-Softmax, you have everything now you need for flash attention. So let's go ahead and start looking at Online-Softmax specifically for attention. So let's go ahead and take a look at Online-Softmax for attention. So like we talked about, essentially to compute this specific vector, we need to do the multiplication of this value, this weight here, and this vector here. This is computed from here, and this specific value here is computed by mapmoling the first query and the first key. So essentially the setup is like this. S1, which I'm going to call this value right here, S1 is Q1, K1 transpose. M1, so this is Online-Softmax because I will not load this whole vector. That's the key idea. I'm not going to load the whole vector. I'm just going to load this one element, as we're going to loop through it one at a time. M1 is the max of S1, and really the max of this one element is just, whatever this element is, because we're going to initialize M as negative infinity, just like we did earlier. Then P1 is going to be e to the power S1 minus at least my current max estimate. That's going to be this right here. L1 is going to be the sum of P1, right? So the sum of exp s minus m, that's going to be my L1, another running statistic I'm going to keep track of. And then O1, the final output, this O1 right here, is going to be this weight, P1, times this specific value vector, V1. And that seems pretty simple. So let's go on to the next iteration. One quick caveat. Why are we doing sums? Because it doesn't really make sense to have all these sums here. It's because later, of course, just like we did in the Online-Softmax, we're not going to look at it one element at a time. We're going to look at it in a block of elements at a time. So in this case, if we had a block size of 2, then we would do the mapmul of the first query and both keys, K1, 2. The max will be essentially the max of both of these elements, not just one of them. So whichever one's bigger in these two things. Our probability is just going to be e to the power each one of these elements minus the max of these two elements in this case, which will give me these two values. And then my running sum is going to be the sum of these two probabilities right here. And then my output, this is going to be the mapmul of these two weights and these two values, right? So of course we're going to do it in blocks later on, but for simplicity, we're going to stick to it in one element at a time. Otherwise it's just more annoying to kind of analyze what's happening here. So in the next iteration, we're going to move on to the second value. So we need the second probability and the second value. For the second probability, we need the second iteration here, which is fine because we're going to loop through this one element at a time. So that's no problem. And to get this specific value here, I need the first query and the second key. So let's do a little bit of analysis here of what's happening and what could go wrong. S2 is Q1, K2 transpose, that's S2. M2, my running max, is going to be, well, if this value here is bigger than the earlier one, then this is my new max. If this value here is smaller than the earlier one, then it's the max stays the same, right? Nothing changes from one element to the next, because again, we're doing softmax along this row, or Online-Softmax along this row. Then the probabilities can be, again, e to the power S2 minus my new max, and then I map mode this, this weight with this value, and I accumulate that into this specific vector right here. But here's the problems. Just like we had in Online-Softmax, L could be wrong. If my max changed from this element to this element, then my earlier iteration, L1, which is based on P1, and P1 being based on M1, if M1 and M2 are different from each other, then my earlier sum was incorrect. This is exactly the same issue we had in Online-Softmax. So L2 is supposed to be the sum of exp S1 minus M2 plus sum of exp S2 minus M2. This is what we want, where M2 is going to be my global max across S1 and S2. In this case are just single element values, so it's not that interesting, but S1 and S2 can also be blocks of values, as we could be looping through it in blocks. But the problem is this, iteration 1 again could have been wrong, because we wanted S1 minus M2. This is what we should have, because M2 is my new max. What we did is S1 minus M1. So if P1 is wrong, then L1 is also wrong. And then of course, if P1 is wrong, O is also wrong, but we'll get to that. We'll get to fixing that later on. So what do we have? M1 is max, P1 is exp S1 minus M1, L1 is the sum of that. What I want is P1 is just exp S1 minus M2, and L1 is the sum of that. So it's again the same discrepancy. This had a max of M1, because that's all I knew then. In that iteration, M1 was my max, but M1 could have been replaced with a brand new M2, my new max. And so this is the same update rule as before. The corrected L1 is same step. We're going to do the sum of exp S1 minus M2. We add and subtract the things, so it's going to be M1 minus M1 plus M1 minus M2. We're going to go ahead and split up the S1 minus M1. We have the M1 minus M2 term, and then we're going to do M1 minus M2 e to the power M1 minus M2. This is that adjustment term from earlier, times sum of exp S1 minus M1. And so we're essentially going to have exp M1 minus M2, the adjustment term, times L1, because the sum exp S1 minus M1 was exactly what we had for our L1. And so this is that same thing as earlier. This is our adjustment term to L1. All we're doing is our original L1 has to be multiplied by this adjustment term to correct it for the fact that M1 and M2 may be different. If M1 and M2 are not different, because the new max in the second iteration is the same as the old max, then this just ends up being e to the 0, which is just 1, so no update. And so up to iteration 2, this is the term that needs to be fixed, and we fix it by just doing this, right? We're going to replace all of this with L1 times exp M1 minus M2. And then we have, of course, the new values here, and the new values will be based on M2, because we're going to compute this right now, so it's okay. We're going to be having all this be correct. And so iteration 2, we fix L, but O, for the same reason, will also be a problem. Remember, our output is based on the probability. The probability is based on S1 minus M1, but M1 is wrong, or could be wrong. M2 could be different. And so in the second iteration, and essentially here's the problem, as we loop through, we're essentially accumulating into this output here. We're going to do this weight times this vector accumulated to here, plus this weight times the second vector accumulated again into that same position. The issue is that when I'm doing this iteration, that first accumulation, so what we had right here, this accumulation, this weight times this vector, and then we move on to the next weight times the next vector, when we move on to the next one, the first one, this one here, this weight times this vector, could have been wrong, because I know this P1 here could have been wrong, because this P1 was based on an older M1. So in the exact same way that we updated our L values, we need to also update our O's. We need to adjust for the fact that our original M could have been wrong. And luckily that's pretty easy. So just like earlier, O1 is P1 V1, which is just P1 is simply e to the power S1 minus M1 times V1. And O1 should have been not S1 minus M1, it should be S1 minus M2. In the second iteration, this is what it should have been, but this is what we currently have. The math is identical. Basically, O1 corrected is just going to be e to the S1 minus M1 times V1. And again, we're going to minus and add M1 and M1 again just like before. We're going to pull out the terms just like before, and we're essentially going to end up with e to the power m1 minus m2, the same adjustment term as before, times e to the power s1 minus m1 times v1. And e to the s1 minus m1 times v1 is what we had earlier. That's O1. So our corrected O should be our adjustment term times O1. And so this is essentially what it's going to look like. L2 is going to be adjusted L1 plus the new term. O2 is going to be my adjusted same adjustment factor O1 plus the new P2 V2. So all we've done is we initially, in the very first iteration, we multiplied some weight by this value here. We're in the next iteration now, we're multiplying the second weight by the second value, and that's this term right here, the second weight times the second value. But in computing the second weight, we have a new estimate for the max. And this estimate, M2, is not what we used in the first iteration to compute M1 or to compute P1. And so essentially all we're doing is we're readjusting our previous iteration to account for the fact that we could have been wrong. And that's exactly what this operation is doing. So this looks really no different. This is the same as the Online-Softmaxes earlier. It's just instead of doing it for the running sum L1, we're doing it for O, but it doesn't change anything else. And of course, yeah, again, that's the new term. And of course, you might be wondering where actually is the softmax, because up till now, we've been kind of just doing probabilities, right? Or we've been calling these probabilities, but they really aren't probabilities. P is just e to the power s2 minus m2, or P3 will be s3 minus m3, so on and so forth. Where are the probabilities? Because we haven't really divided by this denominator. Well, this is just dn, right? This is essentially the final sum exp that we're going to get at the end. So at the end, as we loop through everything, we're going to finally have our true sum. This is just a constant, so it doesn't matter if I multiply it in the mapmul stage or if I multiply it or divide, essentially, if I divide by it at the end. This is just a constant. So if I do it before or do it at the end, it makes no difference when I do it. So I can just do it right at the end. I have ln, so I can go ahead and take the vector here and just divide by the sum exp. And this will be the true sum exp with the global m, because we've completed iterating through all of these values here along the vector. And of course, we need softmax in the backward pass. If you remember, and we're going to see this again in more detail later, but in softmax, when we do the softmax of the vector, we also need those probabilities in the backward pass. And so the trick we have here is for every single vector that we do softmax over, so for every single vector here, we're going to store an m, and this m was our LogSumExp trick. Remember, with this one value here, m, uppercase m, I can quickly recompute the probability of any value in this vector with no issue at all. So we're essentially saving memory because we're not storing some giant probability vector anymore, because the entire point of flash attention is we never realize any of these matrices. I may have drawn everything here, but we only actually compute the pieces that we need. As we're iterating through, I don't really care about the rest of it. I only need the element that we're currently looking at. And so in the end, once we're done iterating, I'm going to store this uppercase m value right here. So in the backward pass, which we'll look at in more detail later, we can then quickly compute the probabilities, and we'll see again why we need that. So we're just going to store these for now. As we saw, we can quickly recompute probabilities from here. Of course, we're going to compute these in blocks. So instead of just doing one element at a time, we might do 2 queries at a time and 2 keys at a time. So this would be like a block size of 2 essentially in both directions. Doesn't really change anything. We'll just loop through and just do it that way. So we're going to start here and then move on to the next one. So, but we can see the pattern here. Basically, the queries we want is the same indexes of the outputs. And then we loop through the inner dimension of the keys and values. And then we're going to do the mapmul of the queries with the keys, grab those weights, compute the attention weights, essentially the attention weights of that sub matrix, the small portion of the attention matrix we're currently looking at. Because here, notice that when we're computing this part here, we don't care about the other values. When we're computing this part here, we don't care about these other values. So we're only loading this part or computing this part in memory. We go ahead and compute the softmax, the Online-Softmax, just like we've talked about. It's just instead of doing one vector at a time, we're going to be doing multiple of them, but that doesn't really change anything in the math. It's mostly just a indexing thing. And we multiply those with the values and then accumulate them up in the positions that we want in the output. So in the Triton implementation later on, the batch, normally our data is batched by heads, number of heads, by sequence length, by embed dim. That's the standard shape for most transformer like LLM problems. And so what we typically do in Triton is we're going to parallelize batch head. So every single PID, every single worker that's get parallelized is they're going to process a individual batch head combination. And then the sequence length is what we're going to loop over to do this entire operation that we just talked about. So no issues there. In our implementation today, because we're not doing it in Triton, we're just doing it instead in Torch, we're going to do a for loop through the batch and head dimension. But of course, that doesn't change anything about the numerical, how the actual numerical formulas or anything like that. It just means it's going to be slower, but we're not going for speed today. We're just going for understanding. There are a couple of small tricks that we need to keep in mind. So whenever we do softmax, we keep saying e to the power, e to the power, e to the power this, e to the power that. We don't actually want to do e to the power because e to the power actually is a little bit slower than doing 2 to the power. GPUs are great at doing 2 to the power stuff. They're not as great at doing e to the power stuff. Luckily, we can adjust it. Remember, this is just change of base formula. So if we have a to the power log b base a, that's just b, standard formula. So if we have 2 to the power log e base 2, that's simply e. So log e base 2 is simply just log e base e divided by log 2 base e. That, change of base, that's simply the natural log of e over the natural log of 2. And natural log of e is just 1, so that's 1 over ln 2. So we can then write e is equal to 2 to the power 1 over ln 2. That doesn't break anything with everything else we've seen here. And if e is equal to 2 to the power 1 over ln 2, that's the same as saying e to the power x is equal to 2 to the power 1 over ln 2 to the power x. And exponents multiply, so x over ln 2 is, we can just write it that way. And so simply, we have e to the x is equal to 2 to the power x times 1 over ln 2. And the trick is this. I don't want to do e to the power something. I simply want to do 2 to the power something. So if I do 2 to the power something, but that something is divided by ln 2 ahead of time, that's the equivalent of doing e to the power something. So this is a numerical trick. All we're going to do is divide our x, or whatever we're doing, divided by ln 2 ahead of time. And so instead of doing e to the power every single time, we're just going to do 2 to the power. And by doing 2 to the power, we're going to get exactly the same values. Numerically, they're the same thing. It just saves us from doing more expensive e to the power operations. We get to do cheaper 2 to the power operations. There are a couple of other small details. So first, the accelerating causal attention. When we're doing our operations here, right? So we're going to grab this chunk of queries, this chunk of keys, that computes this part of the attention matrix, compute the softmax, map mul, accumulate. And this is fine here. We've computed this, but of course we're going to compute this in blocks, and now we're going to go on to the next chunk. Is there any point of doing this iteration? Remember, this is causal attention. All 4 of these positions are grayed out because they're all non-causal. They're all not supposed to contribute to our entire operation because these are positions in the future because they're grayed out. So this technically is just, in the end, all this is end up going to do is we're going to multiply a bunch of zeros by these values and accumulate in. So all we're really doing is just adding zeros and doing nothing. So us even iterating to this position here is a waste of compute because multiplying by zeros is still work. It's just we don't need to do this work if we don't have to. And so to accelerate causal attention, when we have these, the top triangle mask, the causal mask, essentially there's only a couple positions we care about. We care about this one, we care about this one, and we care about this one. These are the only positions that matter. And so the issue is kind of this. Our blocks, when we define blocks, at least for now, they can only be squares. We don't have good sparse matrix operations, at least in PyTorch, just yet. And so because of that, we have 2 cases. We have a case where our block is on the diagonal. Diagonal blocks have the condition where they may have some elements, as we can see here, this element and this element here are invalid positions, but all the other elements are valid. So on diagonal positions have a kind of this causal mask on it. Off diagonal or pre-diagonal positions, everything is valid. We can see all 4 positions are valid here. And so these are the 2 cases. In non-causal, then everything, we attend to everything, so we don't really have to think about it in this case. And so something we have to think about essentially is the block size Q and block size KV. How many queries do we want to grab at once? And then how many keys and values do we want to loop through in block size KV sizes? And the easiest way to look at this is essentially let's just look at a bigger attention matrix here. We have this 8 by 8 attention matrix, and let's say we have block size Q of 2 and block size KV of 2. That means in the first iteration, we're going to grab the first 2 queries, indexes 0, 1, and then we're going to loop through the keys and values 2 at a time. So 0, 1, 2, 3, 4, 5, 6, 7. In the next iteration, we're going to grab queries 2 and 3, and then 0, 1, 2, 3, 4, 5, 6, 7. Again, another one, queries, we're going to grab 4 and 5, then 0, 1, 2, 3, 4, 5, 6, 7. So very simple. This is basically the loop. We're going to loop through the queries in chunks, and then for every chunk of queries, we're going to loop through the keys also in chunks. If we have causal attention, take a look at this. We have a causal mask here, so all of these positions are invalid, which means we essentially have, for queries 0, 1, only this first block really matters. Of course, it's an on-diagonal block, as you can see, so we still have a position here that's invalid, but there's no reason of looping through all of these other blocks here. That's kind of just a waste of compute, because these blocks here, if we loop through these keys and values, they have no contribution, so it's just a waste. Similarly, for here, when we're doing 4 and 5, right, we want to loop through these two. These are, notice that they're fully attention, so there's no masking or anything here. So we have, these are all pre-diagonal blocks, this one and this one, but then this is a on-diagonal block. So this is also valid, but we have one invalid position here. But then there's no point of looping to this last one here. It's just a waste of compute again. So question is essentially, how do we know the indexes? And the indexes are pretty simple. If I'm processing indexes 4 and 5 here, then pre-diagonal keys and values will be everything less than 4. So we can see that up to here, basically, if we're processing indexes 4 and 5, keys and values 3, 2, 1, 0 are all pre-diagonals. Everything less than 4 is pre-diagonal. And then the things that are on diagonal are just the indexes themselves. So 4 and 5, so indexes 4 and 5 are on diagonal. And then everything after 5, 6 and 7, so 6 and 7 are post-diagonal. So those are the ones we don't care about. So we want to kind of keep these things in mind. We're going to see in the implementation that this matters. But we're going to have to keep track of what indexes of the keys and values are the pre-diagonals, which ones are the on-diagonal, and which ones are the post-diagonal that we can just skip altogether. Of course, they don't have to, the keys and values, like these don't have to be squares, like the queries and key value blocks don't have to be 2 by 2. They can also be 2 by 4, but it doesn't change anything, because if you do 2 by 4, well, it's the same idea. We have, these are all my pre-diagonal. This is my on-diagonal, but now in my on-diagonal, we can see that we have some wasted masking happening here. So we're going to have to mask out all of these positions, and we'll see how this is all implemented in just a few minutes here. But that should cover it, right? That is essentially the flash attention algorithm kind of annotated, walking through exactly how everything works. So we're going to use this all as a reference as we're going. I'm going to keep it right here for now, at least. Keep this as a reference, and let's just go ahead and start implementing flash attention using nothing but PyTorch. And this should all start to come together. We're going to do the forward pass first. Once we've figured out the forward pass, then we'll start on the backward pass. All right, so all we're going to need is our torch and math. It's very simple. We're going to do def flash attention forward. And we're going to pass in the queries, the keys, the values, the softmax scale, which will just be none by default. Are we doing a causal system or not? So is causal. We'll set it to false. And then we have a block size q. How many queries do we process in every iteration? 64. And then block size keys values, which we'll just set to 64 for now. And so let's just go ahead and copy a little bit of this in so we don't have to type it. There we go. And then u. Okay. So this is the data shape. So queries and the keys and values are all going to be batch size by number of heads, by sequence length, by head dim. And then the softmax scale is simply just going to be, we can either provide something if you want, but by default, the scale that we're going to divide is going to be 1 over square root of the head dim, right? So that's square root of a dk that we divide by. And the inverse ln2, 1 over ln2 is this value right here. And this value right here is what's going to let us do 2 to the power stuff rather than e to the power stuff. Now, here is the first little trick. In this operation, I never actually drew it, but it is there, right? So when we do the QK transpose and get the attention matrix, technically we have the attention matrix, we then divide it by the constant, and then we compute the softmax, right? So we divide this stuff here by dk. I didn't draw it just for simplicity, but technically, whether or not we divide the values here, like at this point, or if we divide it earlier, doesn't really matter, because this is all, it's just a multiplication. So whether I'm doing QK transpose divided by the constant, or if I do Q divided by the constant and then multiplied by the K transpose, doesn't matter. The order of my multiplications here don't matter, as this is just a single constant. And I actually have 2 different constants right now. I have my square root of dk. This is for the attention operation specifically. But then we also have the inverse ln2. We need to multiply either query or, like we need to multiply an inverse ln2, the 1 over ln2 in here somewhere. so that later on, when we actually go to do our attention matrix, like right here, when we get our attention matrix, these things are all divided by ln2 already. So instead of doing e to the power, I can do 2 to the power. And so when I do softmax, everything will just be 2 to the power rather than e to the power. That's it. So essentially, all of these values here need to be divided by both square root of dk, and they need to be divided by ln2. So we're going to do both of them at the same time. We're going to do our softmax scale times equals inverse ln2. Let's just stack them all together. I have my softmax scale constant that I need to divide by. I have my inverse ln2, which is 1 over ln2, that I also need to divide by. And so I'm just going to multiply it all together, and we're good to go. It's just one constant that has everything I need. And we're going to do q is equal to q times softmax scale. This is just pre-scaling our queries in queries, so everything just works out. And again, this is essentially the line item that I just want to make sure. Query k transpose times softmax scale times inverse ln2, right? Because that's also in there technically, is the same as doing q times softmax scale times inverse ln2 and then map modeling with k transpose. Doesn't really matter when or where we do it, so it's easier just to do it ahead of time. Then we're going to have m. This is going to be torch.full. It's going to be batch size by num heads by sequence length. So let's just kind of get a general idea here. Our data is batch by heads by sequence length by embed dim. That's our queries. And when we multiply this and do our attention matrix, we're going to have batch by head by sequence length because we're going to have that e. We're going to have batch by head by e by s. That'll be our queries. We'll have our keys, just like that. So this is standard attention shapes. And then we're going to qk transpose. And this is going to be batch by head by sequence length, because you have an s by e multiplying with an e by s, so s by s. And what we know is essentially we're going to do the softmax along each row. So in this s by s matrix, let's go back to the figure right over here. Should label these a little bit better, but this should be fine right here. So basically in this s by s matrix, for every single s, we're going to compute one specific value, right? So we're going to compute this m value here that we want to store for later. And so for now, we're going to do for basically every single sample in the batch, for every head, we're going to have sequence length number of these m's that we want to store. And for now, I'm just going to populate them with, it doesn't really matter, float negative inf. We're going to start them off as negative infinity because e to the power negative infinity is just 0. And there we go. Just keep it simple. We'll do device is q.device and dtype is going to be torch.float32. So there we go. So this will be the m matrix that we're going to compute for later. This m, which will populate with values as we actually do everything, will let us quickly compute probabilities later on in the backward pass without explicitly storing all the values. Remember, again, this has L elements in it. L could be 128,000 things. In the backward pass, I need the probability vector. Otherwise, I can't do softmax without the probabilities. But I don't want to store all 128,000 things here because that'd be ridiculous. So flash attention, the main trick is let's store this one scalar value m, and in the backward pass, we can recompute probabilities on the fly. And so there we go. That's m. Then we have our output. This is going to be torch.zeros like q, right? So this is just going to be, remember, the output shape and query shape are all the same. So we're going to just store it like that. And let's go ahead and start the actual kernel. It's not really a kernel, but the formula itself. For b in range batch size. B in range batch size. And then we're going to do for h in range num heads. And these two things is what Triton parallel, right? So this whole for loop that we're doing here is not something we'll need in Triton because Triton will independently, right? Triton will assign a PID, a worker, to do each one of these batch head combinations, and then many of them will happen in parallel. But of course we can't do that here. So we're gonna leave it as a for loop for now because nothing else matters. And so now what we're gonna do is process our queries in blocks. We're gonna do for q start in range, 0 to sequence length, block size q. So we're going to process the entire sequence length in blocks of size q. So this is, again, remember, the outer loop, the outer loop that I mentioned. So let's go back right here. This is our queries in the outer loop, but we're going to process them in blocks. And then for every single block of query, we're going to loop through the keys and values in those inner loops. And that again looked exactly like this, right? So we have our queries and we have our key values is the inner loop. So let's just start with the queries, right? So this is going to be q end is going to be min q start plus block size q sequence line. This is a quick just check, right? Because of course we want to make sure that when we go from q start to block size q, we're not spilling over the max sequence length. We're going to have to do masking and stuff later for Triton, but this is fine for now. And then q indices is going to be equal to torch dot a range from q start to q end device is equal to q dot device. So what are the indexes? Which specific queries are we processing? We're processing query 0, 1, 2, 3. What are we doing? So these specific indices of queries are the ones that we're going to be processing. And then our q block is going to be, it's going to be q. We're going to grab this specific batch, this specific head, and then we're going to grab from q start to q end, and then the entire embedding dim. So this is essentially going to be a block size q, so block size q by head dim tensor, right? Very simple, 2 dimensions. Now we also need, of course, is these running statistics, right? We're going to loop through these. So going back right here, all right, we're going to loop through these iterations, which means we need to initialize some statistics. We have our L and M. Let's initialize them, and then we're going to populate them just like we did in Online-Softmax. So mi is equal to torch.full. And how many elements are we processing? We're specifically going to loop through. Let's go back to the block picture right here. We're specifically looping through, in this case, let's say block size of 2 queries. That means we're processing 2 rows of our attention matrix, like this, right? That's how we're looping through it. And if we're processing only 2 rows of the attention matrix, that means I'm going to have 2 m values that I'm going to compute at the end. So I need 2 running statistics, an mi and a di, one for each row. So block size q, however many q's I'm processing, is how many mi's and di's I need to store as we're going. So mi is going to start off as q end minus q start. We're going to start off just like before, float negative inf, right? This is going to be our max estimate. So we're going to start everything off as negative infinity. Device is q dot device, and d type is torch dot float 32. And then li, which will be our running sum, instead of di, they call it li in the original Flash attention paper. This is the sum, so we're just going to start off as zeros, right? Just start off as zeros, and we're going to quick iteratively add to them as we go. Minus q end. Again, device is q dot device. Oh, and I want to start these off as 0.0. Oh, actually, it's not as 0, sorry. We're fine. Device. And then our d type is torch.float32. There we go. So yeah, that's essentially it, right? We've gone ahead, initialized our running sum, or running max. So in this case, we're processing specifically these 2 rows here, which means I need a running max of this row and a running max of this row. And I need the running sum of this row and the running sum of this row. And I'm processing 2 rows, which is going to be essentially q start, q end minus q start, q end minus q start. And just process them, and that's it. So we've created some placeholders, essentially. Our output block, O block. So if we're processing these 2 specific queries, that means we're going to have 2 specific outputs at the end as well. As we saw, it was, they lined up with each other, right? So essentially, with these 2 queries correspond to these 2 outputs, and we're looping through the inner dimension of the keys and values, right? Keys and values, just like that. So we just need to create some temporary values here, initialize it as zeros. And as we're looping through the inner things, we're going to accumulate, right? Plus equals into those positions, right? Just like that. So O block is going to be simply torch.zeros. It's going to be from q end minus q start, just like before, by head dim. That's the shape. Device is equal to q.device, and d type is equal to torch.float32. So all we've done is initialize 2 by embed dim, or in our case, head dim positions, right, as zeros. And we're going to accumulate into these as we're going through. So that's our output block. Good. So now for the key trick. And so let's go back to this visual here. I am going to loop through my keys and values, but which ones? Do I need to do all of them? Do I need to do some of them? Which ones are pre-diagonal? Which ones are on diagonal? Which ones are post-diagonal? That sort of stuff. If we're doing full attention, we don't care. We just do everything, right? So in full attention, we just do everything and we don't care. So let's start with that case. If is causal. So if we're doing causal, let's just skip this case for now. We'll come back to it. Pass. Else, we're going to do our KV ranges is going to be, we're just going to process everything from 0 to sequence line. And we're just going to call this full. There you go. So we're going to process everything. So our KV, keys and values, are going to go everything from 0 to the end. And so it doesn't really matter. We don't really have any cases or anything here. But in the case of causal stuff, we have these couple of conditions here. So let's go ahead and work on this one. KV ranges. So let's do KV start processing. KV, our keys and values will always start at 0. So we can see everything always, when we start processing keys and values, will always start at the beginning position. But the question is, how far out do we go out? So KV start processing, and then we're going to do KV end pre-diagonal is going to be equal to Q start. So why is this happening? Remember, if we're processing queries 4 and 5, our keys is everything from 0 to 3. The only things that are pre-diagonal is this stuff here. This is on diagonal. All of this is pre-diagonal for these specific positions, which means if we're processing 4 and 5, queries 4 and 5, we only need to process 0, 1, 2, 3 as our pre-diagonal values. And so essentially we're setting our KV end pre-diag as 4, because if we do indexing from 0 to 4, that's really just 0 to 3, as Python is not right inclusive in indexing, right? So essentially, our end pre-diag is wherever we're starting here, 4. That's it. Then we have our KV start diag. This is going to be the diagonal block. The diagonal block is simply, in this case, we can see it's 4 and 5. So it's going to be 4 and 5. It's going to be 4. Q start. And then KV end diag is going to be Q end. Now, of course, in this case here, we did a block size of 4. So I just said that the start and end is from 4 to 5, but I'm going to be processing them in block size of 4. So even though I just said that these are the only two diagonal positions, when I go and actually block it, I'm going to index over extra, because I only really need these two, but I index over extra, which means I end up grabbing more keys than I actually need. I compute more keys. And so I need to make sure I mask out all the invalid positions later on, which will happen in just a second. So now our KV ranges is very simply, the first range is going to be KV start pre-diag, sorry, not pre-processing, we're going to call this pre-diag. There we go. KV start pre-diag to KV end pre-diag, and these are going to be called the pre-diagonal. And then we're going to have our KV start diagonal, KV end diagonal, and these will be our diagonal blocks. And that's essentially it. So our KV ranges are either one single tuple that just goes from 0 to sequence length that we're going to process in block sizes of KV, or we have two separate tuples. The first tuple going through just the pre-diagonal indexes, which we're going to loop through in block size KV, whatever the block size KV is, and then a secondary tuple that will only be for the diagonal block that we're also going to loop through in block size KV. It's just in this case, it kind of works out very nicely because, if we do it 2 by 2, it's kind of nice and neat, but as we increase the block size, right, we can see that it'll change up a little bit. So that's fine. So that's essentially it. So now what we're going to do is for KV start range, KV end range, pass type in KV ranges, right? So we're essentially looping through these tuples. So start, end, and what kind of pass are we doing? Is it pre-diagonal? Is it diagonal? Is it everything? And then what we're going to do is actually loop through these indexes in chunks of size block size KV. So we're going to do for KV start in range, KV start range to KV end range. And then we're going to do in chunks of block size keys and values. Then we're going to do KV end is equal to, just like before, KV start plus block size KV up to KV end range, right? So we're essentially just going to loop through in chunks, but we don't want to really exceed this here. So this is us handling the exception that, oh, maybe it doesn't work out and we have some extra values. We don't really care. This is going to be handled a little bit better when we do the Triton stuff later on. So, how we do it in Triton is of course going to be slightly different, but that's the main idea. We've gone ahead and computed the end, which is either the full block or just up to the end of whatever it may be. And then we're going to have kv indices is going to be equal to torch.arange. It's going to be from kv start to kv end. Device is q.device. Make sure it's all in the same place. Then we're going to actually load our data. So k block is going to be the keys. For this specific batch and head, I want from kv start to kv end. And I want the entire embed dim. And then our v block, v, it's going to be the same thing. For the values, we want this specific batch, this specific head. I want kv start to kv end. And I want the embed dim. So this is us loading the specific block. So let's go back right here. To get this specific chunk here, for example, I need these specific keys and these specific values. So I've gone ahead and loaded them. In the next iteration, I'll have to loop through, right? So this is just a looping operation. So do you need this one or the next one? And we're just going to loop through the keys and values in chunks of whatever the chunk size that we selected is, right? Very simple. So we've loaded the keys and values. So we essentially, again, the algorithm is the outer loop. We loop through a bunch through our queries in chunks. And then for every chunk of query that we load, we go ahead and loop through our keys and values also in chunks of block size kv, but only through the valid positions if we're causal or non-causal, right? For efficiency purposes. So qk block is equal to. So what we're doing now is I need to actually compute the qk transpose for this specific block. Well, that's going to be the queries I have already map mold with the keys. For the previous iteration, it'd be the queries, same queries as before, map mold with a separate set of keys, right? So on and so forth. So whatever we're doing the map mold between the queries and the key transpose. So let's go ahead and do that. qk block is going to be equal to q block at k block transpose, qk transpose. So this will end up being a block size q by block size kv, right? That's the shape of that little tensor. And here is our little sanity checks. If we are on a diagonal block like these, some positions in this block are invalid. And so we need to make sure we deal with that. And the way we deal with that in standard attention is we fill invalid positions with negative infinity. So when we do the softmax of it, it'll end up becoming e to the negative infinity. It'll zero it out for the actual softmax values. So let's go ahead and do that. We'll do if pass type is diag. If we're specifically on a diagonal block, again, we've indexed that out here. We've identified that this is a diagonal block. If we are on a diagonal block, we just need to handle that condition. Our causal mask is equal to, and let's kind of take a look here. So if we're looking at, let's say, these positions here, this is in queries 0, 1, and then keys 0, 1. So we're going to treat the queries as a column vector because you can see it goes along the column, and then the keys and value indexes as a row vector. So our indexes for the queries will be 0, 1, and the indexes for the keys and values will be 0, 1. And so the question is this: where are our queries greater than the keys and values? Because if the query positions are greater than the keys and values, that's good. That means they're valid, right? So we want to make sure that the query is always greater than or equal to the keys and values we're attending to. So that means query 0 can attend to 0. So let's just do the check. So 0 can attend to 0. That's true. Is 0 greater than or equal to 1? No, that's false. Is 1 greater than or equal to 0? Yeah, so that's true. And is 1 greater than or equal to 1? Yeah, that's true as well. So that creates the true for these three positions and false for this one position right here. Just like you see here, true, 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 and a false. And so that's all it is. So the causal mask just identifies in this small block size q, block size k, like this little chunk right here, what positions are valid and what positions are invalid. And we know this one top right corner, this one right here, is invalid because this specific query at position 0 can't attend to a key at position 1 as that's looking into the future. And that's essentially it. So our causal mask is simply just going to be q indices. This is just a vector, so we need to make it a column vector. just like we did. So this is basically going to be block size q by 1. So block size q by 1. And we're going to see wherever it's greater than or equal to our kv indices. And this is going to be none by 1. This is, or 1 by blank. So this is now a row vector. And this is just the operation that I just did. Which indexes in this column are greater than or equal to indexes along this column. And that's it. That's our causal mask. Now what we're going to do is our qk block is equal to qk block dot masked fill. We're going to flip the causal mask. I'll explain why in just a second. And fill in with float inf, right, negative inf, just like our standard attention setup. The reason we're flipping the mask here is because we have these as true and this position is false, but masked fill will fill the true value and ignore the non-true values. So only for the masked position, so we're going to go from true to false to everything here false to true, flip the mask, and then fill it with negative infinity, and we're good to go. That's our standard setup. We also have, and we don't really need this right now, but kv padding mask. This is technically unnecessary. So if we do kv indices less than our sequence len, we technically don't need to do this right now because we've already handled it here. Our kv end ends at kv end range, and kv end range can't go past our sequence length, right? That's not possible because the max it could be a sequence length. So this is technically not necessary, but we'll need it in the Triton kernel later, right? So we're going to just leave it in here for just to make it one-to-one with the implementation we'll look at in the future. Mask fill, kv padding mask, again, none, blank, just as a row vector, 1 by, block size kv, float, negative inf. Basically, if any of our keys and value positions are invalid because, we don't have perfect coverage or basically round it up, all the keys and values, like let's say our valid position was up to 8, but our block size kv was like 5 instead of 4. So the first block would have processed 0 through 5, and the next one would have processed like 6 through 10, which means positions 8, 9, 10, everything afterwards would have been invalid. So all those invalid positions, wherever our kv padding mask, where the kv indices are less than sequence len, wherever they're invalid, so we flip it just like for the same reason we did it right here, fill them with negative infinity, which essentially fills those entire columns with negative infinity. Basically anything that's invalid that would have been right here, fill them with negative infinity, just so we're good to go. I don't really care about that right now, but that's there because technically we handled it already, but we're going to need to do this in Triton later. So it makes it one-to-one. Okay, indexing is done. Let's go ahead and actually do our Online-Softmax. So mij is equal to torch.maximum. We're going to compare mi to qk block.max dim equals 1.values. So for this specific block, right, so we're on like, let's go back to a better visual. Let's say we're looking at this specific block right here. We've gone ahead and we found the max of this row and this row for this specific block. And then in the next iteration, we'll find it for this specific block. So all we've done is find the qk block, find the max along the rows for every single row. So this is basically a vector of length block size q, and then compare that to mi. And mi, again, remember, is also a vector of block size q. So we're just doing a vector-wise operation. This is a vector of what I think the max is for this row. This is the vector of what my max is for this specific block, and I just update them accordingly. So I'm basically doing a row-by-row update here. And then qk block is equal to qk block minus mij. Remember, qk block is a block size q by block size k. mij is block size q, and that's it because it's just a single number. So we're going to add an extra dimension here just to broadcast correctly. So now it's block size q by 1. So when I subtract it from here, it's going to subtract from every single element in this block. We're going to go ahead and do that. So essentially, we've found some max for this specific block here, whatever it may be. Let's go back right here. We found some max, and now we're going to subtract every single element in this row by the max that we have for this row, and every element in this row for the max, whatever we have in this row. So it's just an element-wise, again, operation. Then we have our probability block. P block is going to be equal to torch.exp2, right? Because we've done the update to make it exp2 instead of exp, qk block, and that's basically it, right? So we've gone ahead and exponentiated it. So if we go back to our actual formulation. So that was right over here, right? We've gone ahead and done e to the power s minus m2, and we just did s minus m2. So that's s minus m, did e to the power. That gives us our probabilities, at least for up to this iteration. And then our Lij is going to be equal to p block, right? So it's the p block dot sum. We just need to do the sum of what we have up till now. So it's going to be p block dot sum dim equals 1, right? It's pretty simple. That's our L is just the sum of those exponentiated s minus m2. And again, we're going to do this per row. So we're going to, this Lij is again just going to be a vector of size, just like Mij is going to be a vector of size q, whatever the block size q is essentially. And then our alpha, this will be our correction factor, will be torch.exp2, like before, mi minus mij. That's the correction factor, m1 minus e to the power m1 minus m2, e to the power m1 minus m2. These are our correction factors, and we're going to need them to update L2 and O2 in the next iteration. So that's our alpha. And so now, of course, Li is equal to Li times alpha plus Lij. Is that what we have? Remember, our update for L is the correction factor times what our L currently is plus the new L. Lij is what my new L is. Li is what my original L is. So I'm multiplying Li by the alpha as something could have been wrong. My original max estimate could have been wrong. This updates it, and I add the new term on, and that gives me my new Li. And that's essentially it. Very simple. And that gives me my Li. In the same way, we need to update our O. So O block is going to be equal to O block times alpha. We need to make sure we add the extra dimension in. Again, O block is going to be in the shape of batch size, or not batch size, the block size q by the embed dim. Alpha is simply just going to be block size q. So we're going to make it block size q by 1, as we're going to need to update this along the entire output. So basically the extra exp m1 minus m2 that we have for this row, we need to multiply to the entire row, not just to like one element of the row. So we need to multiply the whole row. So we just add that extra 1 dimension so it broadcasts correctly. And then we're going to add on to it the new O. So that's simply going to be p block at p block. So that's this, right? The output is going to be the adjustment term times the original output plus the new block, the new PV, just like that. And that goes ahead and gives us our final output block. And then at the end, mi is going to equal to mi is equal to mi j. Just update my running max for the next iteration. So we just start this all over again, right? So basically, we're just going to rinse and repeat this over and over and over again. For every single block of queries, we're going to loop through chunks of keys. And for each chunk of key, we're going to go ahead and compute this stuff. And that's it, right? That's the entire, that's it. That's basically flash attention, right? So we can see it's really not that bad. We still have a couple of extra little steps here. So the first one, of course, is we want to store, we could technically store Li and Mi separately. So Ln and Mn, the global max and the global exp sum. But like we saw in the LogSumExp trick, there's no need to do that. It'd be cheaper for us to just store them as a single value just for efficiency purposes. So we're going to exit the loop. So essentially, once we're done for this specific block of queries, so once we've only finished this block of queries, let's go ahead and actually update our values here. So essentially, for this chunk of queries, let's say, we've gone ahead and computed everything. So we've completed looping through this iteration. So like here. So once we've completed this iteration, loop through all, for this specific chunk of queries, all the keys and values, we're at the end of this. We've computed the softmax iteratively of this row and this row. So now we just want to store the m for every single one of these rows. So we can go ahead and do that right here. So that'll be, double check. I think that's in this loop. Yes. So yeah, at the end of this one. So what we're going to do is mi LogSumExp is simply going to be mi plus torch.exp2 li, just like before. And then inside m, for this specific batch, this specific head, for this specific chunk of q start to q end, as we're processing, we process that many of them, it's going to be mi LogSumExp. And that essentially just goes ahead and does this. So for example, in the first chunk of our, let me find it. right here. So for essentially, we processed 2 queries. So we've computed the m's for both of these rows. So we're going to go ahead and store both of these m's. In the next iteration, we're going to process the next 2 queries. Then we're going to process these 2 m's, so on and so forth. So that just goes ahead and saves everything for us. Of course, we also need to do the one other sanity check, or not really sanity check, but the normalization. We actually never divided by ln. So let's go ahead and do that here as well. O block is going to be O block divided by li. Add that extra dimension on, so we do it along the embedding dimension as well. And we'll just add a little thing here so you don't accidentally divide by 0 or something like that. And then in the final output for this specific batch, for this specific head, for this Q start to Q end, along the embedding dim, we're just going to store this output block. Right, just go ahead and write it. And that's essentially it. We've gone ahead and accumulated here. We've created a thing, accumulated it, and now we're just going to write this to our final output block. And that's essentially it. Return O and M. So let's go ahead and give this a quick test. So we're going to do this. We just create some data. And what we're going to do, these are a little bit short. Let's make the sequence length like 1024 or something. Just so our blocking actually has some blocking to do. And we don't need DO right now as we haven't done the backward pass, so ignore that. And we have our OM is going to be our flash attention forward, QKV, and whether or not we want it causal. And for our comparison, we're going to be running the torch's own scale dot product attention. And what we're hoping to see is the difference between our output and the PyTorch's output should be the same. So very similar. So our output versus, or the PyTorch output versus our output. Let's go ahead and see how this works out. Looks like we have a bug. So received an invalid combination of arguments. So let me check. Mi is torch.full. So let's see here. How is torch.full supposed to be used again? I just used it incorrectly. I am missing float negative inf. Oh, these are supposed to be tuples. I always forget that. This is a tuple already. Okay, let's see if that works. Okay, almost there. So our alpha is incorrect. Size of tensor A, O block, okay. O block is going to be Qn minus Q start. Let's check here. Print O dot shape. What are we looking at here? 64 by 0 by 64. What do we do? Oh, made a mistake there. Now let's see. There we go. So we can see very minimal difference. 4.2 e to the negative 6, right? So very small diff. And so this essentially is the flash attention algorithm. Our own code will essentially look like that when you do it in Triton. In Triton, 2 things will be happening. The batch and head dimension will get parallelized. Different PIDs will be responsible for different batch head combinations. And then for the rest of this stuff, essentially, we're going to have an outer loop, and then we'll have the inner loop, and that'll be written as 2 separate Triton kernels, and basically the outer loop is going to call the inner loop. That's basically it, right? So relatively straightforward. So the forward pass is actually pretty easy. The backward pass has quite a bit more going on, but we're going to work through it. So let's go ahead and get started with the backward pass. Now that we've completed the forward pass, we're going to be working on the backward pass. And the backward pass is essentially this. The attention mechanism takes in some queries, keys, and values and produces some output. So given the derivative with respect to the output, we want to find the derivative with respect to the queries, keys, and the values in the backward pass. And this is just a little bit of shorthand. When I say the derivative with respect to the output, that's really the derivative with respect to the loss. With respect, so DLDO, derivative of loss with respect to the output, essentially the upstream gradient to this operation. And essentially given, remember, QKV went into creating O, so we need the derivative of the loss with respect to Q, derivative of loss with respect to K, and derivative of loss with respect to V. And so essentially this is what it looks like. In the forward pass, we had the QK transpose, we computed some softmax, we had some probabilities, we had some values, produced an output. That means in the backward pass, we're going to have gradients for each of these tensors. dO for those, dV for the values. We have dP through the probabilities, ds through the s. We have dk for the keys, and dq for the q's. We'll have a little bit of it. Remember, we use k transpose, but what we really want is dk, so we're going to have to do an extra transpose. We'll see all that come together in just a bit. But that's it, right? Basically, given the forward pass, we need the derivative of these three things. And what we'll be focusing on is, where do we even get the derivative for these three things? So let's kind of break this up a little bit. Let's say the output is p times v. P is the softmax of s, and s is qk transpose over the square root of the embedding dim. This just lets us quickly kind of do some sanity check of where did these derivatives even come from? So as a reminder for matrix derivatives, if you have C as a map mold with B and G is dLdC, your upstream gradient, then the derivative of loss with respect to A is G B transpose, and derivative of loss with respect to B is A transpose G. This is just your standard matrix derivative rules, right? So just keep this in mind as a template, because essentially we're doing all of this. For example, if we have O as P times V, the derivative with respect to V, right, so dL dV, it's going to be P transpose dO. And then if I want the derivative with respect to P, that's going to be dO times V transpose. That's just using exactly these rules, right? So it's using these standard derivative rules, just applying to O equals P times V, where upstream gradient is dO. And so this is easy. We can compute dV and we can compute dP. dV is one of the things that we actually needed, right? So that's kind of looking positive. We also need the derivative with respect to Q and K. And so we said S is equal to QK transpose. We also have the square root of the embedding dim in here, but it's just a constant, right? So for now, I'm just going to keep it out for shorthand, but we'll just add it in the implementation because it's just a simple numerical constant, so nothing fancy. So dQ is equal to ds K transpose transpose, right? So again, following the formula, ds K transpose transpose, that's just going to be dQ is equal to ds map mold with K. And then dk transpose transpose, because remember, we actually want dk. We don't really care about dk transpose. So dk transpose transpose is equal to q transpose ds transpose. And so dk is equal to ds transpose q. So just write these out if you want, right? This is just, again, this is just applying this formula to finding what's the derivative with respect to v and p, and what's the derivative with respect to q and k. So just write these out. It'll be self-obvious, just applying the formula directly. The problem is this. Where do we actually get ds? Like, I need ds here, and I need ds here. I need ds, but I can't get ds, because to get to ds, I need to do dp ds. I need to derivative. I need to take the derivative, the chain rule, through the softmax. Going back to the beginning here, right? Look at the chain rule. I need to go from output to the probability, output to the v. I need to go from p to s, so dp ds. Then I need to go from ds dq to and ds dk. That's the chain rule. In this chain rule, how do I go from P to S? And that's really the main annoyance with the backward pass for flash attention. Because remember, for S, we technically need the Jacobian, but we saw in our MyTorch video, which I, again, will implement down or post down below, where we do the hand derivation, we find a non-Jacobian variant of it. So this is the vectorized form of the gradient of a softmax. And the gradient of a softmax, you need the probability. P is the output of the softmax. dP is the upstream gradient. dP is no problem. We can get that right here. dP is just dO times V transpose, right? So we have everything there. So that's looking good. We have another dP, and then we subtract, and then we do the dot product of dP and P. So this is everything. And for the most part, this looks harmless, but there are some issues. So first, dP, like we saw earlier, is just dO V transpose. And so if dP is dO V transpose, can we compute dP pretty easily? Yeah, we can, because dO is something we have. dO is something we have ahead of time. This is my upstream gradient. V, my values, is something I already have. So that's no problem. The issue is that dP is equal to, if dP is dO V transpose, that's L times embed dim, map mold with an embed dim times L, producing a full L by L matrix. This is exactly the same problem as the forward pass. To compute the entirety of dP would mean that we'd have a full L by L matrix in the backward pass. And that would mean that we'd have, if L was 128,000, that's again 128,000 squared elements. Luckily, this actually isn't a problem. The reason is that I don't need to compute all of dP. I don't care about all of dP. I just need the piece that I need. For example, if I need this specific element of dP, I can quickly compute it from DO and V transpose. Just grab DO, V transpose, and I'm happy. So I don't need to compute all of DP. I'm going to just compute the piece I need. Just like the forward pass, we're going to apply these same tricks to the backward pass. Can we just not compute stuff that we don't need and just keep it minimal to the stuff that we do need? So again, remember, how do we get P? That's another big question. Like, how do we actually get P? Remember, in the forward pass, we stored this thing. We stored this thing for the LogSumExp trick. This will allow us to quickly compute probabilities if I want this specific probability. Right? If I need the probability of this value here, because again, remember, let's go back right here. I need P. I need my probability. Okay, fine. If I need my probability, how do I get it? If I need the probability of this specific element, I know that that's going to be e to the power this minus the LogSumExp of this row, right? Basically, I computed an m. I have an m that I've computed ahead of time of this specific row. So if I do e to the power this value minus that m, whatever that constant is, that will give me this value directly. That's the real power of the LogSumExp trick. So where do I get this value from? Well, it's easy. I can get that from Q and K, right? If I do the query times the K transpose, that gives me this value. I can then do e to the power this value minus that LogSumExp, the constant that we saved, and that lets me quickly recompute probabilities. So basically, those are the two tricks. To compute DP, we can go ahead and compute exactly the piece of DP we need based on DO and V transpose. So that piece is there. If we need a probability, which we also need, that's also relatively easy. If I need this specific probability, I just need this specific value of the QK transpose. And then using M, my LogSumExp trick, I can quickly recompute my probabilities without explicitly taking a softmax again. That's exactly why we created this M in the first place. The problem is not P and DP, it's rather this dot product. Because if I want the dot product of DP and its corresponding probabilities, that means I need all of P and all of DP. And this is, once again, a problem. Just like before, we need the entire row for me to do the dot product. So is there another way to do this? And there is. So let's think about it this way. This dot product is really the sum from 1 to L of dp ij times pij. So I'm going to do this element times this element plus this times this, this times this, this times this, so on and so forth. But we can do better. We know that the output is equal to, the output here is P L by L times V, right? That's our standard formula. That's how we set it up. And technically, this, remember, this vector here of the output is simply the matrix multiplication of my weights of here with all of V. So it's basically these, again, it's this first weight times the first vector plus the second weight, second vector. And that's what you see here, basically the weights times the corresponding vectors. And this is what we can do. dp is, for a specific dpij, we saw was just do v transpose. This is exactly what we saw just a few slides ago, right? dp is simply, we can grab a do, the corresponding v, and we can quickly recompute the probability or the derivative of the probability that we need given just do and v transpose. Okay, so that's what we can do. What we want is dp ij times the probability of ij. Well, if I can quickly recompute this stuff, I clearly see a substitution here. What happens if I substitute do v transpose into here? That's pretty straightforward. So we can go ahead and do dpij times pij. It's simply just pij times the thing I substituted, do v transpose. And notice that this sum here is on j. It's from j from 1 to L. So this O is indexed with I, right? Basically which query are we on? And the j is which key value are we on? So this technically is not a part of the sum. We can pull the doi out. And we're left with probability of ij, v transpose. But what was that? Was that not just oi? Oi is the sum of probability times v transpose. Let's go back to that slide again. Our output, where did it go? Here, output, right? The output, the specific output is the probability times the value, right? The probabilities, weight probability times the values. That's exactly what this is. The probabilities times the values, just summed up. And so really, this whole annoying probability, multiplying the derivative of the probability, dot product with the probability, basically the dot product between these two vectors, can be reduced down Just simply doing a derivative of the output times the output, just multiplying those rows together. And this is very convenient because I have this and I have this already in memory. So this is not expensive. This would have been insane because this would have been an L length vector multiplied by another L length vector for each L length vector because we have an L squared operation. So this would have been huge, but it's been reduced down to something very simple. And this is typically called like the pre-processing step for the backward pass. And so simply, I have my output, I have my derivative of the output. Let's just go ahead and multiply those values together, and that gives me this new constant called di. What do I do with di? Di is essentially just used right here. That's what this value is. The sum of basically the dot product between dp and p is simply just di. And so my derivative with respect to s, I can quickly recompute the probabilities, no problem. I can, using my LogSumExp trick, I can quickly compute the derivative of the probabilities, like we saw. But now I can also, I don't have to deal with this entire annoying dot product anymore. I've already pre-computed some di that I can now use. That's essentially the entire novelty of the backward pass. So let's start at the top. We need dv, dk, and dq. So let's start with dv. dv, like we said, was p transpose do. And I know if I need the probability in p transpose, I need the probabilities. I have an easy way to compute probabilities. That's just going to be e to the power, the s of the element that I care about, minus the LogSumExp trick, basically my LogSumExp trick to quickly compute probabilities. And I can quickly compute s based on the q and k. So essentially that's the pathway. If I need a specific probability to multiply with do, no problem. I first need to grab what's the index I care about. I multiply the qk transpose for that. I apply the LogSumExp trick to quickly compute the probabilities, and then given those probabilities, I can then multiply with do. So this is kind of the chain of operation. This is again allowing us to, instead of storing a giant L by L matrix for S or a giant L by L matrix for P, I'm quickly recomputing exactly what I need on the fly. And there's a trade-off, right? By recomputing stuff, we're using more compute, but by recomputing stuff, we're not having to store giant things in memory. And memory is really the issue here. It's not really the compute, as all of these are relatively simple operations. And so here's what it's going to look like. In the forward pass, we have qk transpose, all of this stuff. And in the backward pass, we have all of this stuff. And what we really care about right now is dv. That's what we're looking at. dv, that's why I've whited it out. And we're going to essentially accumulate gradients into here. And so this p transpose right here, let's just kind of take a look at it this way. Let's see. Yeah. So basically all we're going to need is this. So to compute our setup here, all we need is queries and keys. So we're going to need the q and k. We're going to need the s and our m's, which are just constant that we computed. So you can't see the m's here, but they're there. So we need the s. We also need to compute the probability. So these probabilities here are based on the s. And of course we need dv, and we need our dv, and we need our do, the upstream gradient, right, do. So essentially, to compute dv specifically, these are the only pieces we need, and the rest of the stuff we don't care about right now. So let's just look at the simple version of it. dv is simply p transpose do. So this specific vector, let's just look at one vector of dv. This specific vector of dv is equal to p transpose do. How does that work out? I need to do the p transpose, this vector, multiplied by do. Now, I've done one small thing here before we keep going. Earlier, we've actually gone ahead and flipped some stuff, because notice that this is p transpose. So what we don't really care about p, we need p transpose. So if I need p transpose, that's the same as doing the softmax along s transpose, right? Along basically the columns in this case. And to get s transpose, qk transpose gives me s. So kq transpose, if I flip them around, right? So qk transpose gives me s. So qk transpose, the whole thing transpose, is kq transpose, gives me s transpose. So I've just flipped things around just for simplicity, but that's the only little thing. So we have kq transpose. Kq transpose gives me s, and then s transpose I can do to get p, and so on and so forth. And what I need is the probabilities of these specific values right here. I need the probabilities that I need to do p transpose multiplied by all of do. This vector here, map mult with this matrix. That's no problem. If I need this vector, I simply need these values right here. So I need to do KQ transpose, the first key with all of the queries. That gives me this vector. And then I can go ahead and do my LogSumExp trick to get the actual probabilities for these values, right? That's the entire point of the LogSumExp trick. We're going to go ahead and grab those. And then once I've computed probabilities on the fly, notice that we've basically recomputed what the probability should be. We can then go ahead and map mul with the DO and get that specific vector. And that's the trick. And essentially what it's going to look like is an iterative algorithm. We're just going to loop through piece at a time. So to compute the values, we simply grab a key and we loop through the queries. So for a specific key, notice the key and the DV and the key have the same index here. We're looping through the queries. This is backwards of what we did in the forward pass. In the forward pass, we grab a specific query and loop through the keys and values. Now we're doing it the other way around. We're grabbing a key and looping through a key and value essentially and looping through the queries. Very convenient, right? So this is essentially the main trick for the backward pass. Of course, we're also going to have some extra things here, like don't do extra stuff for causality. So our causal mass now is underneath. It's flipped around because this is S transpose or P transpose. So essentially when it used to be a top right triangle, now it's a bottom left triangle, right? So but it's the same thing, right? It doesn't really matter. It's just because it's a transpose, it's flipped around. But in the same way as earlier, we want to make sure that when we're looping through these iterations, we're not doing stuff with because again, the causal mass, if we apply the causal mass, we're just multiplying by zeros, which is just a bunch of like pointless computations, right? We don't need to multiply these values by zeros. It's just wasted operations. And so we're going to have to do the same thing, but where in the forward pass, we had essentially the pre-diagonal and the diagonal values. In the backward pass, we're going to have the diagonal values and the post-diagonal values just because everything's been turned around here, right? We've flipped it around and we'll see that come together later. Dk. How do we get dk? So dk, again, remember, is ds transpose, map mul with q. We need ds. We had an easy way to compute ds, right? That was this entire trick where we've computed some d value. We can easily compute dp on the fly by doing do times v transpose. And we can quickly compute probabilities also on the fly using the same formula as earlier. So I can recompute derivative of s quickly and get to q. So that's the pathway, right? So I've pre-computed these. These di's are constants that I've already saved ahead of time. This I can compute on the fly like this. This I've already computed on the fly in the process of computing dv. We also needed probabilities there. That lets me compute ds ij on the fly and then go ahead and map mul to get the q. And just like before, we have the pij, we have the di. And so what do we need? We kind of need everything. So essentially, to compute this vector of dk is again ds transpose. So I've drawn it as ds here instead of, it flipped around just for some simplicity, but just to keep it clear. So we need not ds, like a vector of ds, we need ds transpose, which would really just be grabbing this vector as I then draw it transposed here, ds transpose. And we're going to map mul this with all of q. So to get this specific vector, we need the map mul of this vector and all of q. And again, very simply, it's just going to be a simple loop through of the elements, just like that. We're going to loop through them. Of course, we're looping through them one element at a time. Later, we'll be doing them a block at a time, just like we did in the forward pass, but same concept. To go ahead and actually get our setup, though, is a little bit more complicated, right? We need to get these DSs, right? So, of course, we need to do the map mul. Where do we actually get these DSs from? Well, that's pretty easy, right? We know that ds is equal to the probability of ij times the derivative of p minus di. And I know the derivative of p is equal to do times v transpose. So let's just go ahead and take a look. To compute this specific ds, I simply need to do my derivative, or let's start at the beginning actually. We first need the probability, right? We need these probabilities here. To get the probability, this specific probability right here, because I need a corresponding one, right? So if I want ds ij, the top left corner, I need dp, or I need p ij, top left corner. And to get this, I simply need this value here, so I can do the LogSumExp trick to get there. And then to get this value, I just need to simply multiply the first query and the first key. So that's the pathway through this first one. Then to compute dp, I need to do this stuff. So to get dp, I simply need to compute my do, this vector right here, times my vj transpose, right? The dot product essentially between those two things. And then I can go ahead and subtract the di, which I don't have here shown, but it's just a constant that I've computed ahead of time, right? So it's simple. And so essentially to compute dk, this is the whole pathway. This is all the pieces of data we need. And as we loop through, this is what it's going to look like. So essentially what you can see here in this loop, to compute a specific dk, we grab the corresponding v, and we're looping through the queries, right? We're just looping through the queries, as you can see here. And again, just following through the path is exactly this, right? We have essentially to compute the ds, to compute ds, we need the probability, which we've done before. To get this probability, we just simply do the map mul of these two, get this value, LogSumExp Trick, we can quickly compute that on the fly. Di is just a constant that we've already pre-computed, we apply it, we're done. To get the dp, we simply map mul the do times the vj, so this vector times this vector. And again, this simply just lets us loop through and do it that way. So those are all the pieces that are contributing. I would highly recommend drawing this out once for yourself, just so you can piece it together, as there's a bunch of stuff going on. In the same way, so if you've noticed, basically for dk and dv, there's a bunch of commonalities. Like for some key and value index, we loop through the queries and we always need these probabilities. So it's kind of convenient to do them all at once. So we can actually compute the keys and values at the same time. If we want this specific value here, dv, I need all of these pieces of information, just like we saw earlier. If I want this specific key here, I need all of these pieces of information to compute it. And so essentially, there's an overlap. This stuff here, the entire process of computing probabilities is the same, right? We need them both for dv and dk. We need to compute these probabilities. So we can do that once and just share that information between the two operations. I need a do is of course always the same, it's upstream gradient. And then in the process of computing dk, we have some extra pieces of information. In the process of computing dv, that's pretty straightforward. That's all we need. And so essentially what it'll look like is this, right? To compute dk and dv at the same time, we're just going to loop through our probabilities one at a time, probably transpose essentially, computing everything we need on the fly, and then just looping through the corresponding do that you see right here. So this is basically what the operation is going to look like. We're just going to loop through piece by piece, and we're essentially just following the formulas, but this is just identifying which parts are being indexed. And by doing this iteration, we can go ahead and actually accumulate up the dk and dv contributions from everything else. That's it. So that's the trick. Of course, we're going to do this a block at a time, right? So it won't just be one at a time, it's just a block at a time. But for simplicity, we're just going to keep it one at a time. We could also have causal masks. So when we do this operation, we're going to make sure that, we look at the post diagonal and diagonal values, just like we did before. To compute dq is a lot of the same. So first, to do dsk, to compute this specific vector of dq, we need this vector of ds and all of the k's. And then to compute all this stuff, well, how do we get ds? This is the same setup as earlier. To get ds, we need the probabilities. We need to do probability times the derivative of probability minus the di. So this is the same setup as before. We still need to compute all of the probabilities, which means we need all of that information. We need to compute the dp, which is simply, again, the derivative of the output times the values. So it's the same setup as earlier. Computing dq is a lot of the same thing. The only difference now is that to compute dk and dv, we basically picked a specific key value and looped through the queries. Now we pick a specific query and loop through the keys and values. And that's really what changes, right? So that's why we can't do the dq, dk, dv all at the same time, because they fundamentally loop through different things. To get dk and dv, we basically loop through all the queries and accumulate up all those contributions. To get the dq, we loop through the keys and values and accumulate up all of their contributions. And so it's just fundamentally different. So nothing changed. When computing dk dv for a specific kv, we loop through all the q's. For dq, for a specific q, we loop through all the kv. And that's it. It's just backwards. Again, in the same way, we're going to have to loop through in block sizes because we want to be efficient about it. So let's just go ahead and implement it. Implementation is a lot of the same. It's really not too complicated. It just has a little bit of nuance. So let's copy a couple of things here. So a lot of the same thing as before, but we're going to pass in a couple extra things. So we have dk, we have qkv, we have the output. This is the output we computed at the end. We have our derivative of the output. This is the gradient from upstream. And then we have our m, which is the LogSumExp. So this is all the stuff we've computed. And then everything else here is the same, block size Q and KV. And then we have our batch size. This is the shape of the data. That softmax scale is the same as earlier. And we have the inverse ln2, so that's important. But we also have ln2, which is basically 1 over inverse ln2. And this essentially will let us unscale the scaling that we applied, right? Because scaling was only to make sure that everything stayed consistent. That let us do 2 to the power stuff. But when we exit it in the backward pass, we need to make sure we unscale the things because we don't need it anymore. So just like we did before, softmax scale times equals inverse ln2, because that's the scale we multiplied by. So remember, I didn't really talk too much about the, let's actually just keep out. Yeah. I didn't talk too much about the actual, like when you do QK transpose, we divide by a constant. And that's because when you do the gradient if you multiply something in the forward pass, we have to multiply by the same thing in the backward pass. And so this is the thing we multiplied by in the forward pass. We're going to multiply by the same thing in the backward pass. Right? We're going to keep it simple. So to actually do this, let's go ahead and just apply that same. We applied the scaling in the forward pass, so we need to make sure we have the same thing here, softmax scale. Just so everything's equivalent, otherwise it wouldn't work. And we're going to initialize some gradients, right? And so we're going to initialize the gradients as dq, dkv, dv are just going to be tensors in the shape of qkv, and they're going to start out as zeros, and we're going to accumulate them up as we go. Now, first step, of course, is our little trick. So let's go back right here, part 1. Sorry, Canva had like a limit of how many elements you can have in a slide deck, and apparently I broke it, so I had to split this into 2 slides, but that's okay. We have right here, let's see here. Yes, so this was the quick trick that we had. Basically, we need this value right here, again, from our softmax, for the derivative of the softmax, but we didn't want to compute it, but we had the trick. We can do this. So we're going to do the derivative of O multiplied by the output of O, and that will give us everything we need. So we call that D. This can be torch.sum do times O dim equals -1. This is basically along every single vector, every single embed dim, go ahead and multiply them, and that looked like this, right? Basically grab this and do the dot product, and then grab this and do the dot product. So we're just going to multiply element wise and then add up all the rows, and that should be enough. And this will be in the shape of batch by our num heads by our sequence line, right? And so let's go ahead and start. So we're going to do first dk dv, and I'm actually going to paste stuff as we go for some of the doc stuff, so I don't have to type all this out, but it'll make it clear. So we have step 2. We need to first compute dk dv. Step 1 was this, computing this. So dk dv, so dv again was p transpose do, and dk was ds transpose q, right? So those were our formulas. So let's go ahead and start. So again, just like before, for batch or for b in range, batch size, for h in range num heads, right? So again, these are the 2 things that Triton would be doing in parallel, but we're doing a for loop for simplicity. And like we mentioned, in the computation of dk and dv, we pick a specific key and value, and then we loop through the queries. It's basically backwards of what we had done earlier. So we're going to do for kv start in range 0 to sequence line in block size kv. We're going to do kv end is going to be min kv start plus block size kv up to the sequence line, right? So this is us making sure we don't spill over. Again, just like before, we'll handle this better in Triton later on, but for now it's fine. And then our kv indices, which indices is going to be torch.arange from kv start to kv end, and device is equal to q.device. Very simple. And then our k block, which block of k are we loading? It's going to be keys, this specific batch, this specific head, from kv start to kv end. And then the v block is going to be values for this specific batch, this specific head, from again kv start to kv end. Very simple, right? So we've gone ahead and loaded everything, and just let's reference the figures as we are going. We need, yeah, so right here. So essentially, we're going to be looping through. So we're essentially grabbing a single key, or a block of keys in our case, and a single value, or a block of values. And we're going to be looping through the queries, which we haven't gotten to yet. We'll get to that in a second. But that's essentially the operation, right? That's the essential operation. We're grabbing a block of keys and a block of values. And that's us grabbing a block of keys, block of values. We then have our dk block is equal to torch.zeros. So this is going to be the accumulator. We're going to basically, as we loop through the queries, we need to accumulate the gradients into something. So this is what we're going to be accumulating into. I'm just going to paste this because I don't want to type it. Pretty straightforward. It's basically for this specific block from kvn to kv start. So that's us initializing a empty dk for this specific vector or a block of vectors, and as this specific dv or a block of dvs. For a block by embed dim, go ahead and initialize some zeros so we can accumulate gradients into those specific positions. And this is the important part. So we're doing if is causal. So first of all, else, if we're not causal, then quranges is equal to from 0 to sequence len. That'll be full, right? Just if we're not causal, then we don't really care. But if we are causal, then we want to care a little bit. We're going to do quranges diagonal is equal to, well, what is it going to be? It's going to be from kv start to kv end diagonal, right? That's basically what it was just like last time. So again, looking at our forward pass, the diagonal block indexes didn't change. It's still from the kv start to kv end. So what positions are we currently looking at? Our quranges post diagonal is equal to, this is going to go from kv kv end to sequence len post diagonal. And this is basically what changed. Earlier in our forward pass, we went from essentially our pre-diagonal from 0 to the starting point. But now the post diagonal is basically the end of our key values to the end. And that's exactly what we're doing here. If we have a attention, causal attention, our limits are not at the beginning. We really just want to loop through the diagonal block and the post diagonal stuff. And so the diagonal blocks are this stuff right here, and the post diagonal is everything afterwards. And that's just a computational save, that we're not computing stuff on pre-diagonals like this position right here, which is just 4 gray values, right? These are all 0, there's nothing here. And so that's all it is. And just to make this all the same, let's just put it all in one list for simplicity, and we'll call these quranges. Right, so this is the same as before, same concept, except now we're going diagonal and after the diagonal rather than the diagonal and before the diagonal, as everything is transposed. Okay, so what we're going to do now is loop through our queries. There is one, of course, like one thing we're doing KQ transpose. We actually haven't done the Q transpose yet, of course, because we haven't loaded Q yet. So we're about to do that. Right now we just have K and B. We're going to do for Q start range, Q end range, and pass type in Q ranges. For Q start in range, from Q start range to Q end range in sizes of block size Q, just like before. Everything else is kind of set up in the same way. So I'm going to copy a little bit of this so I don't have to type it. So basically, what is our ending point? Q end. We have our Q indices. So for this specific block of KV, we're now going to be looping through chunks of our queries. That's exactly what we saw right here, right? We're just looping through chunks of our queries, just like that. So we have our, for a specific key value looped through our chunks of queries, right? So now that we have that, those are the indexes of the specific chunk of queries we're loading. And let's go ahead and load everything now. So our Q block, I'll also go ahead and paste this because we actually need a couple pieces of information. We have our Q block, so batch head, Q start to Q end. We need our D output block. Remember, we're not just looping through our queries, we're also looping through DO, as you see right here. So as you see right here, we're looping through DO in the same way. So we need to grab that corresponding block of D output as well, no problem. That's DO. We then need to grab M, remember, we need essentially, this is S transpose. So we computed originally, before we did the transpose, the softmax along each one of these columns, essentially, right? Every one of these columns, which used to be rows, every one of these columns, we computed the softmax, which means we have an M value for every one of these columns. So the question is, for me to compute this specific probability, I need to take this value here, which is the operation of this K, Q transpose, and then do the e to the power of this value minus the M, the LogSumExp for this specific column. And that will let me compute this probability. So I need to go ahead and grab the M's for this specific chunk as well. So basically block size Q values of M, because if I'm grabbing these two Q's, then I need the M's for these corresponding blocks. If I'm grabbing these two Q's, then I need the M's for these two corresponding blocks. In the same way, I also need my D block, right? Because the D block, remember right up here, batched by num heads by sequence length for every single value for every single operation, going back right over here. The number of D's, basically the number of outputs and number of queries, they are aligned to each other. So right here, remember, we basically have the one-to-one correspondence, and just like we had earlier, right over here, for every single query, we're indexing the corresponding output, which means we need the corresponding D value that was this specific output that corresponds to this query with, this specific D output with this specific output. And for the next one, it'd be, for this specific query, it'd be this specific D output dot product with this specific output, so on and so forth. So this is, again, just all indexing things to make sure we're just grabbing the right pieces of data when we need them. That's all this is. So that's me just loading all that data right up. And now let's just go to the formulas. So S T block is going to be K block at Q block transpose. So that's my K Q transpose, K Q transpose. So this essentially just gives me my S transpose directly, because that's really what I care about. And now what I need to do is recover my softmax, recover the probabilities. So I have S now. I need to recover the probabilities for the S's that I've just computed. Well, that's no problem. I can do P transpose. Of course, it'll also be transpose because S is transpose. It's going to be S T block minus M block. Remember, those are my LogSumExp Trick values. None, blank, because this is going to be a 1 by, so this is going to be block size KV. So this can be block KV by block Q. M block, as we see, is just block Q. So I need to make it 1 by block Q. So I can apply a 1 by block Q to a block KV by block Q, and this 1 will broadcast over this dimension. And so it's going to be P transpose is going to be that minus the M. Very simple. And of course, it's not just that. It's going to be torch.exp2, exp2 again, because I've already adjusted for it right up here, right, by multiplying by a scale. And this will let me go ahead and quickly recompute the probability. So I had this, and now I have probabilities. And that's how awesome the LogSumExp trick is, because given this one little constant, I can recompute probabilities on the fly rather than having to store some giant probability matrix. Of course, now we need to do our quick check. So if pass type is diagonal, okay, then our causal mass, this is going to be the same as before. So I'm just going to paste it in because this is the same as before. For the diagonal block, all we're going to do is check, are the KV indexes less than Q, right? Because those are my diagonal. And in this case, remember, it's KV is less than Q, where earlier, our pass type was Q greater than KV. It's the same thing, right? Same thing. Nothing really changed. We're doing Q greater than KV is the same as saying K less than Q, so it doesn't matter. But this is going to be a block size KV. So block size KV by 1 less than 1 by block Q. That's why we just did in the opposite direction, so the shapes matched up, because our tensor here, this final output is going to also be block KV by block Q, so our mask has to be block KV by block Q. And then we go ahead and fill those positions, invalid positions, with a 0 in this case. Now the question is, why 0? It's because in the forward pass we fill them with negative infinities because we're going to take a softmax, and then the softmax will essentially take the negative infinities and turn them into 0. But in the backward pass, I've just recomputed the probabilities on the fly. This means invalid positions. I know invalid positions, the gradient of invalid positions the gradient contribution of invalid positions, that is, should be 0. These should be 0. So I'm just going to fill them with 0 because I know that's what they should be. And that's it. If we had done the softmax again, they would have essentially been zeroed out. That would have meant we felt these values here with negative infinity, filled these values with negative infinity, done the softmax, I guess, along the columns in this case because it's transpose. And after doing the softmax, that would have produced zeros here. But we want to avoid doing a second softmax, as we can do the LogSumExp trick to quickly recompute stuff. We recomputed everything, and now we're just going ahead and zeroing out these invalid positions because they should have 0 gradient contribution. So that's it. If we had done the softmax again, we would have just done it like we did before. Because we're not doing softmax, we're good to go here. dv block plus equals. So what was our formula for dv, if you remember? dv is p transpose do. So I have my p transpose. I have do already from earlier, right? That was loaded earlier. So we're good to go. We have do right there. So we have p transpose, we have do. So let's go ahead and just apply it at do block. And we're going to accumulate those gradients in, right? Because again, this is an inner loop, and each of these inner loops have some kind of contributions. We're just going to loop through, do those contributions to dv over and over again. And then we also need to compute our gradients for k. Okay, so dp transpose block is equal to v block at do block transpose. So remember, let's go ahead and find the formulas. I should have put everything on one sheet, to be honest, but that's okay. We're going to find it real quick. So we're looking for this right here. Actually, are we looking for that here? We are looking for dp transpose. So we're looking for dp. So dp was right over here somewhere. That's ds dp. So yeah, that's do v transpose. So we have the output do v transpose, but we don't want dp. We don't want dp. We want dp transpose, like everything's flipped around. So this would have essentially been do at v transpose, the whole thing with the transpose on it. So that's v at do transpose. So again, ab transpose is b transpose a transpose, right? So that's just the trick we're doing here. So that gives me dp transpose block, which is just, again, just the transpose of this. So transpose of this is just v do transpose, just like we have here, just to keep everything the same. And now what we need is the derivative through the softmax. That's our ds transpose block. And this was the main trick, right? This was the struggle that we had. We needed to somehow compute the gradient through the softmax. But luckily, we found our little trick for that. The derivative of s is going to be the probabilities, which we've already computed, times the derivative of the probabilities, which we just computed, minus this little constant that we've already pre-computed, di. Makes it very easy. So ds transpose is going to be p transpose block times dp transpose block minus d block. And we have to add that extra dimension for the same reason as earlier, as this is going to be 1 by block size q. This is block size kv by block size q because it's transpose. And so this is going to just broadcast that one dimension with block size kv. So same reason as earlier. And then ds transpose block is going to be equal to ds. So here's the extra thing. In the forward pass, we multiplied by our inverse ln2. We need to now go ahead and unscale it because we're essentially done, right? So we need to go ahead and unscale it. So it's going to be ds transpose block times ln2. So this accounts for the fact that the ln2 factor from exp2 versus exp, we just need to adjust for it. So we've now adjusted for it. And then dk block plus equals. So what was the derivative with respect to k? It was ds transpose at q. Good. So we can do that. It's going to be ds transpose block at q block. And that's basically it. So that follows all the formulations that we just saw here. That's the dv. Here's dk. So dk is ds transpose q. To get ds transpose, we had to essentially do all of this stuff. We computed the probabilities. We computed our derivative probabilities. And we're good to go. So it seems like a lot's going on, but you can see the math is actually not that complicated. It's just a little repetitive. That's really all it is. So now in dk, for this specific batch head from kv start to kv end, we've computed dk block. Like we've computed a block of derivative, essentially this specific dk dv block. We've started them as zeros and iterated or looped through all the queries, how they contributed to this specific key value, and we've accumulated them all into here. And now that we've accumulated them, let's go ahead and save them in our final derivative matrix. dv for this specific batch head combination from kv start to kv end, it's going to be equal to dv block. And that does it for the first step, right? That is essentially our computation of dk and dv. Of course, that's not where the story ends, because we still have one more. We need to compute the derivative with respect to dq as well. And like we saw, computing the derivative for dq was essentially identical. It was identical because we don't really have to do anything different other than where earlier we picked a specific key value and looped through the queues. Now we're going to pick a specific queue and loop through the keys and values. So it'll be just like the forward pass essentially, but we're going to use the same setup. So we can actually go ahead and just do this. So again, we're going to have to loop through the batch head. So we could make another for loop if we want, or we can just nest it all in here. So let's just put it right here. Yeah, right here. Okay. Let's do this. So we're going to do for queue start in range from 0 to sequence len to block size q. So essentially we're going to be looping through our sequence length in these block size queues because we need to pick a chunk of q first. So I'm going to copy stuff as this is all identical code as earlier. So what's the q end? What are my indexes of q? What is the block that I'm grabbing? So q, d, o, m, and d. And we have our dq. Remember that dq is ds at k. And to compute ds, we're going to have to go through the same process, right? Just like we did here. Here we needed ds transpose. Now we just need ds, so we don't have to worry as much. If we're doing causal or non-causal, this code is all the same. If we're doing causal, right, it's the same idea. We have the pre-diagonal and diagonal. Why are we back to pre-diagonal? Well, because to compute dq, like we saw right over here, to do dq, we don't need to transpose anymore. We're not working with S transpose, we're working with normal S. And if we're working with normal S, then the causal mask is in the normal place. If we were working with S transpose, like we were earlier, then the causal mask flips around and we have to kind of deal with that with the other direction. But because the causal mask is in the same place as we're just dealing with standard S, we don't need to worry about it anymore. Good. So let's go ahead and do that. So basically, same as before, we have our 0 to q start for pre-diagonal, q start to our q end, diagonal. Otherwise, if it's full, it's full. So same as earlier. And then we just loop through our keys and values. So all of this is also the same. So I'm going to put all this down there. Right, so go ahead, loop through our keys, or loop through the pass types, loop through the keys in blocks of size, blocks kv, block size kv, and then load our kv block. So again, we have a chunk of q, and now we're looping through the k's and v's in chunks. It's exactly the same thing, and let's just follow the formula. S block is equal to q block at k block transpose, right? So this is standard S, rather than doing kq transpose to get S transpose, like we had done earlier, right? Kq transpose, right over here. We don't need S transpose, we just need standard S, because our formula says that. We have, like we saw, dq is just ds at k, right? So let's just compute S. We don't need to find the transpose of it. And then our p block is equal to torch.exp2 S block minus m block none. So again, this is going to be, this is block size kv by block size q. This is block size q, so we're going to do block size q by 1, so it broadcasts over the second dimension. So we kept doing it on the first dimension earlier, because block size kv was the first dimension. Now block size kv is the second dimension. So essentially that's the dimension we're broadcasting over. So nothing really changes, same, but it's p block. And so that goes ahead and computes our probabilities using the LogSumExp trick. We then have our pass type. This is the same setup as earlier. If it's a diagonal block, some positions are invalid. Wherever the queries are greater than or equal to the keys, these are invalid positions. And this again flips it around. So again, in the key value computation, when we were doing this. We were doing kv less than q because we needed the shape to be block size kv by block size q. Now we're doing q greater than kv because we need the shape to be block size q by block size kv because, you know, we no longer have that extra transpose. And then p block is just going to be, again, if these are positions that are invalid, then in the backward pass, these should have 0 gradient contribution because we're not recomputing the softmax where the negative infinities become 0 because of the softmax operation. So we just manually set them to 0 just so we don't have to worry about them. They have 0 contribution. And then dp block, dp block, not dp transpose, just dp block is going to be do block at v block transpose, right? So again, this is going back to our dq formulation right here. dp is just going to be do times v transpose, just like we had earlier. So we've gone ahead and computed the probabilities, or the derivative of the probabilities for this specific block. And then our ds block, this is us computing our derivative through the softmax, which will be p block times dp block minus d block. And again, we're going to have to add the extra dimension to the end. That's our derivative. And this is simple ds rather than all the ds transpose and stuff we had to do earlier. And that's it. And lastly, we have ds block is equal to ds block times ln2. We're undoing that scaling. Same reason as earlier. We multiplied in the forward pass. We need to undo it in the backward pass so everything's adjusted correctly. And then dq block is going to be that plus equals ds block at k block, because that was our formula, right? That was the dq is ds matmul with k. So that's all it is. And so that's essentially the setup. Not too bad. And now that we have that, we can go ahead and do dq block is equal to dq block times the softmax scale, because if we multiplied q by some constant in the forward pass, we need to make sure we multiply it by the same constant in the backward pass, so we scale it correctly because the gradients are going to be scaled in the same way. And then dq for this batch, head q start to q end range, it's going to be equal to dq block. And finally, we can return dq, dk, and dv, because that's everything we computed. And that's essentially it. So let's first verify that this is even working, and then I will do a quick recap of everything, and then we'll be done. So you can see it's not too bad, unless I have a horrendous amount of bugs in here right now. Who knows? Okay, looks like we do have some bugs. So let's go ahead and chase them down. So let's see here. What could have gone wrong? There's always something. Let's check here first. Oh, this should be log 2, right? Because the LogSumExp is the m plus the log of those sums. Otherwise, it doesn't work out. Let's see if, hopefully that was the bug. We'll see. And yep, there we go. So yeah, so now we get basically very close reconstruction of the forward and backward pass of our flash attention. So that's essentially it. So if this is confusing, I would recommend going through this a couple times, going through my figures a couple times, and just making sure you really understand what's going on. I hope the visuals help, because without that, honestly, the paper itself did not make any sense to me when I looked at it the first time. But yeah, so this is essentially, again, it's supposed to be an annotated flash attention. We're going to use this code as a reference as we're writing the actual Triton code, because they're going to essentially look identical. There's really going to be no difference between this code and the Triton code, except for the fact that like we have to do a little bit of fancier indexing stuff, because we'll be working with pointers and all that sort of stuff. And of course, we need to make sure we parallelize on the batch and head dimensions. But that's essentially it. The entire novelty, let's do a quick recap here. Yeah, recaps are always good. The entire novelty of flash attention is we are wanting to do the entire attention mechanism, both the forward pass and the backward pass, without ever realizing a massive L by L matrix. We don't want to actually create in memory an L by L matrix. All of these tricks that we looked at, and they're relatively simple, like math tricks, like we did it. There wasn't really that much going on. all of these tricks are essentially just recompute the stuff that we need on the fly, getting everything we need in place to recompute things on the fly as we need them, essentially computing pieces of the attention matrix. And then the question becomes, well, if I need this piece of the attention matrix, what other pieces of information do I need? If I need this piece of the derivative of the attention matrix, what other pieces of information do I need? And by just computing or recomputing things on the fly, we're able to get essentially better processing over long contexts with minimal memory usage, or not minimal, but much less memory usage. And so that's essentially it. That's the flash attention algorithm. I will stop it here. If you have any questions, comments, concerns, please put it down below. This is a pretty challenging, but I think very rewarding implementation because it's so important. And again, like we saw, it's relatively simple. If you look at the actual figure for flash attention, let me actually pull that up right now. There are some differences between how we did it versus the actual original flash attention one. Like in flash attention one, the very first implementation, they essentially do the outer loop is actually the keys and values, and the inner loop is the queries, where we did it the other way around. We did the outer loop as the queries and the inner loop is the keys and values. Both of them work, but flash attention 2, which is the newer version, does the outer loop as the queries, the inner loop as the keys and values, and then they moved on to like flash attention 3 and 4, which are more, those are less about the formula or like the algorithm that we just covered, and more about just leveraging new technologies available in newer GPUs, like the Hopper system has some capabilities, or like Blackwell system has some capabilities, and I think they like supported the new Qtile stuff that like CUDA 13 supports. So it's not really about the actual math or implementation. It's more just about leveraging new technologies that NVIDIA keeps releasing so we can make these operations even faster and faster. So that's basically it. I'm going to call it here. The next video will essentially be just doing exactly what we did in Triton. It should be relatively straightforward. The Triton implementation will cover a couple of extra really cool things. I can show that right now. We won't really go into the code, but we can look at it looks like a lot. I promise it's not. It's a lot of repetitive stuff, so don't worry about it. The flash attention implementation is going to go past a couple things. So first of all, the flash attention, I'll mention this in the next video again, just for commenting. These are 2 awesome resources. Go ahead and take a look at them. I think both of them have videos too. So awesome resources. My Triton implementation won't be, I want it to be a little bit different and helpful. More helpful on top of these implementations, like at least add something new to them. So I'm just not making another video just like everyone else is. So what we're going to do is add a couple extra things to it. Namely, we're going to enable custom attention masks, which these 2 implementations, as far as I remember, don't have. And then we're also going to enable group query attention, which we briefly talked about at the very beginning of this video. But GQA is a really important part of a lot of architectures today, like Llama and whatever else it may be. So we want to make sure our flash attention implementation also supports that. For the most part, the Triton flash attention, and this has been well documented by even the official implementation from the Triton folks. The forward pass is about as fast or even faster than PyTorch's SDPA, which is cool to see. The backward pass is not as fast, and I'm not totally sure why, but maybe it'll get better over time, but it has something to do with the compiler. And the way it, like, basically we have a bunch of for loops, right? So it can only be so fast because we're depending on the compiler, and we don't really have warp level control or anything like that, like we would do if we actually wrote it in CUDA. But maybe I'll make that another video another day, like writing an actual CUDA implementation of flash attention, if anyone's interested. But either way, I'm going to call it here. If you found it useful, comment down below. Again, if you find any of this useful, please do become a member. It's really helpful to support the channel and all that sort of stuff. But I will see y'all in the next one.